Hello viewers of Araatech. In today's video, we are diving into the essential topic of reinforcement learning and its crucial role in shaping artificial intelligence. We will explore how intelligent agents follow instructions to optimize for rewards. This video is a follow-up to our Artificial Intelligence Complete course, where we are systematically covering each aspect of the artificial intelligence curriculum, making sure our viewers can easily understand the concepts. Feel free to ask questions, subscribe for more informative content, and show your support with likes and shares. Thank you once again for joining us on the insightful journey. Let's start our topic. Understanding reinforcement learning definition. Reinforcement learning is a type of machine learning where an agent learns to make decisions by interacting with an environment. The agent receives feedback in the form of rewards or penalties, guiding it to improve its decision-making process over time. It's like teaching a dog new tricks through a series of rewards for good behavior. Basic concepts. Agents. Agents are entities that make decisions within an environment. In reinforcement learning, this could be a robot, game-playing artificial intelligence, or any system designed to learn and act autonomously. Environments. Environments represent the surroundings or context in which the agent operates. For a game, the environment is the game world. The agent interacts with the environment to learn and optimize its actions. States. States are specific situations or configurations within an environment. They provide information about the current context, helping the agent decide what action to take. In a game, a state could be the position of the player and the enemies. Actions. Actions are the decisions or moves that an agent can make in a given state. In a game, these could be moving in a certain direction, jumping or attacking. Rewards. Rewards are numerical feedback that the agent receives based on its actions. Positive rewards encourage desirable behavior, while negative rewards discourage undesired actions. In a game, scoring points or losing health could be examples of rewards. Policies. Policies are strategies or rules that the agent follows to determine its actions in different states. The goal is to learn an optimal policy that maximizes cumulative rewards over time. Role of a machine learning engineer in reinforcement learning. Problem definition. Identify real-world problems where reinforcement learning can be applied, such as autonomous driving or game playing. Data collection. Gather data from the environment to train the reinforcement learning model. This could involve simulations or actual interactions. Model design. Create a model architecture that represents the agent's learning process, incorporating neural networks or other algorithms. Training the agent. Implement algorithms that allow the agent to learn from its interactions, adjusting its policies to maximize rewards. Evaluation and fine-tuning. Assess the agent's performance, identify weaknesses, and fine-tune the model to improve decision-making. History of reinforcement learning. Understanding the historical context provides insights into the evaluation of reinforcement learning. Early concepts from 1950s to 1960s. Reinforcement learning traces its roots to early ideas in cybernetics and learning machines. Researchers like Arthur Samuel worked on machine learning concepts. Markov decision processes, MDPS. In the 1970s, the formalization of MDPS laid the foundation for reinforcement learning. This mathematical framework describes decision making in stochastic environments. Temporal difference learning, 1980s. Temporal difference learning algorithms such as Q-learning emerged in the 1980s. These algorithms contributed to the development of RL in dynamic environments. deep reinforcement learning in 2010s. The 2010s witnessed a surge in deep reinforcement learning where neural networks were integrated with reinforcement learning algorithms. This led to breakthroughs like deep Q networks, DQN, and AlphaGo, ALPHAGO. Recent applications in 2020s. Reinforcement learning is now applied in diverse fields, including robotics, finance, and healthcare, showcasing its adaptability and growing impact. By understanding these fundamental concepts, the role of a machine learning engineer, and the historical journey of reinforcement learning, you will be well equipped to delve deeper into the exciting world of reinforcement learning. Mathematics fundamentals. Probability. Importance. Probability is the likelihood of events occurring. In reinforcement learning, it helps understanding uncertain outcomes and guides decision making. Example: think of rolling a fair six-sided die. The probability of rolling a specific number like A4 is 1 over 6. Statistics. Importance. Statistics aids in analyzing and interpreting data. In reinforcement learning, it's crucial for evaluating the agent's performance and making informed decisions. Example: if you are tracking a game playing agent's scores over time, statistics help identify trends and improvements. Linear algebra. Importance. Linear algebra is the language of vectors and matrices, essential for representing and manipulating data in reinforcement learning models. Example: when defining states and actions, linear algebra helps express them as vectors, simplifying calculations. Programming skills. Programming language Python. Importance. Python is widely used in the machine learning community for its readability and extensive libraries. It is the go-to language for reinforcement learning implementations. Example: writing simple Python scripts allows you to grasp the basics like printing messages or performing basic arithmetic operations. NumPy library. Importance. NumPy simplifies numerical operations in Python, making it easier to work with arrays and matrices. Crucial for reinforcement learning applications. Example: using NumPy, you can create arrays representing states and actions, performing operations like addition or multiplication. TensorFlow, PyTorch. Importance. These deep learning frameworks facilitate the implementation of complex neural network architectures for reinforcement learning models. Example: with TensorFlow or PyTorch, building a neural network for your reinforcement learning agent becomes more manageable, enabling efficient training. By developing a solid understanding of these foundational mathematical concepts and honing your programming skills, you will be well prepared to dive into the practical aspects of reinforcement learning. These skills act as the scaffolding for construction and comprehending advanced reinforcement learning models and algorithms. Markov decision processes, MDPS. Theoretical framework. Importance. MDPS provide a formal structure for modeling decision-making problems in reinforcement learning. They consist of states, actions, transition probabilities, and rewards. Example: imagine a robot navigating a grid. The states are different positions on the grid. Actions are movements. Transition probabilities represent the likelihood of reaching the next state, and rewards could be penalties for collisions or bonuses for reaching a goal. Value functions. State value function definition. The state value function measures the expected cumulative future rewards from a given state, indicating the desirability of being in that state. Example: in a chess game, the state value function assesses the strategic advantage of a particular board configuration. Action value function. Definition. The action value function evaluates the expected cumulative future rewards when taking a specific action in a given state. Example. In a card game, the action value function helps decide the best move by estimating the potential rewards of each possible action. Policy. Definition and role. Definition. A policy is a strategy that guides the agent's decision making by mapping states to actions. It defines how the agent behaves in the environment. Example. In a maze solving scenario, a policy dictates whether the agent turns left or right based on its current position. Exploration versus exploitation. Trade-off concept. Importance. Exploration involves trying new actions to discover their effects, while exploitation involves choosing known actions to maximize immediate rewards. Balancing these is critical for effective learning. Example. Consider an online recommendation system. Exploring new products helps discover user preferences, but exploiting known preferences maximizes short-term user satisfaction. By grasping the principles of Markov decision processes, understanding the role of value functions, appreciating the significance of policies, and recognizing the exploitation trade-off, you gain a foundational understanding of key concepts in reinforcement learning. These concepts lay the groundwork for implementing and optimizing reinforcement learning algorithms to solve diverse real-world problems. Q-learning basic algorithm. Description. Q-learning is a foundational algorithm for reinforcement learning in discrete action spaces. It learns a Q value for each state action pair, representing the expected cumulative reward. Example. In a grid world game, Q-learning helps a robot learn the optimal action, move left, right, up or down in each state or reach a goal. Deep Q networks, DQN. Introduction to deep learning. Context. DQN extends Q learning by employing deep neural networks to handle complex state spaces and continuous environments. Example. In playing Atari games, DQN can learn directly from pixels on the screen, making it adept at more intricate tasks than traditional Q learning. Policy gradient methods. Continuous action spaces. Definition. Policy gradient methods directly optimize the policy, making them suitable for problems with continuous action spaces where traditional Q learning might be impractical. Example. In a robotic arm control scenario, policy gradient methods help learn a policy for smoothly varying actions like joint angles. Actor critic methods. Hybrid approach. Description. Actor critic methods combine aspects of both value-based critic and policy-based actor approaches. The critic evaluates actions while the actor suggests new actions. Example. In playing a game, the actor suggests the next move and the critic evaluates how good that move is. This dual approach enhances stability and efficiency. Additional advice. Progressive learning. Recommendation. Start with Q learning for a solid understanding of fundamental concepts before moving to more complex algorithms like DQN, policy gradient methods, and actor critic approaches. Example. Just as you master basic arithmetic before diving into advanced calculus, progressing through reinforcement learning algorithms builds a solid foundation. Real-world application. Encouragement. Apply these algorithms to practical scenarios like game environments where results are visually intuitive before transitioning to more abstract or industry-specific problems. Example. Use Q learning to teach a virtual agent to navigate a maze before tackling complex tasks like autonomous driving using DQN or actor critic methods. By exploring these key reinforcement learning algorithms in a progressive manner, you will build a comprehensive understanding of how different approaches address specific challenges, starting with simpler algorithms and gradually moving to more sophisticated ones, ensure a smoother learning curve and better retention of concepts. Examples in daily life, recommendation systems, description. Online platforms use reinforcement learning to personalize recommendations based on user preferences, enhancing the user experience. Example, streaming services suggest movies or shows based on a viewer's past choices, encouraging continued engagement. Game playing. Description. Reinforcement learning is widely used in developing intelligent game agents that learn to play and improve over time. Example, chess programs like AlphaZero employ reinforcement learning to learn optimal strategies, leading to sophisticated gameplay. Robotics. Description. Reinforcement learning plays a crucial role in training robots to perform specific tasks by learning from trial and error. Example, a robot vacuum learns to navigate a room efficiently by receiving rewards for successful cleaning and penalties for collisions. Industrial applications, finance. Description. In finance, reinforcement learning is used for portfolio optimization, algorithmic trading, and risk management. Example, an algorithm learns to make investment decisions by considering past market data and adapting strategies based on profit and loss. Healthcare. Description. Reinforcement learning is applied in healthcare for personalized treatment plans, drug discovery, and optimizing hospital operations. Example, an reinforcement learning system helps determine optimal dosages for individual patients based on their response to treatment, minimize side effects. Autonomous systems. Description. Reinforcement learning is integral to the development of autonomous vehicles, drones, and other intelligent systems that navigate and make decisions in dynamic environments. Example, self-driving cars use reinforcement learning to adapt to different road conditions, improving safety and efficiency. Additional insights, continuous learning, observation. Reinforcement learning systems in daily life and industries continuously learn and adapt to changing circumstances, improving their performance over time. Example, your email spam filter refines its understanding of what constitutes spam based on your interactions with incoming emails. Cost efficiency, observation. Reinforcement learning applications in industries often aim for cost efficient solutions by optimizing processes and decision making. Example, manufacturing processes are streamlined using RL to minimize energy consumption and maximize production output. By recognizing reinforcement learning applications in everyday life and diverse industries, you gain a holistic view of its impact on decision making, optimization, and adaptability. Understanding these real world examples provides valuable context for both the capabilities and potential challenges of RL in practical scenarios. Deep reinforcement learning, neural networks in reinforcement learning. Description. Deep reinforcement learning, DRL, involves integrating neural networks into reinforcement learning algorithms, enabling the handling of high dimensional state spaces and complex relationships. Example, deep Q networks, DQN, use neural networks to approximate the Q value function, allowing for more sophisticated decision making in games or simulations. Policy gradients with deep networks. Description. Instead of relying on value functions, deep reinforcement learning also includes methods that optimize policies directly using deep neural networks. Example, Trust Region Policy Optimization, TRPO, and Proximal Policy Optimization, PPO, are algorithms that leverage deep networks to optimize policies for continuous action spaces. Multi-agent reinforcement learning, cooperative and competitive agents. Overview. Multi-agent Reinforcement learning extends the principles of reinforcement learning to scenarios where multiple agents interact and their actions affect each other. Example, in a cooperative setting, multiple drones might collaborate to achieve a common goal. In a competitive setting, agents might compete for resources or territory. Coordination challenges. Coordinating actions among multiple agents introduces challenges such as communication, competition, and negotiation. Example, in a traffic management system, multiple autonomous vehicles must coordinate actions to avoid collisions and optimize traffic flow. Transfer learning, leveraging knowledge across tasks. Definition: transfer learning in RL involves using knowledge gained from one task to improve the learning process on a related or different task. Example: an RL agent trained to play one type of game may transfer some learned strategies to another game with similar dynamics. Pre-trained models application. Pre-trained models on a related task can accelerate learning on a new task by initializing the model with useful knowledge. Example, a language model pre-trained on a large corpus of text can be fine-tuned for specific language-related tasks with smaller datasets. Additional considerations: sample efficiency. Importance: advanced RL techniques often address the challenge of sample efficiency, aiming to achieve effective learning with fewer interactions with the environment. Example, model-based RL approaches use learned models of the environment to plan and make decisions more efficiently. Exploration in continuous action spaces. Challenge. Deep RL faces challenges in exploration when dealing with continuous action spaces, where the space of possible actions is vast and requires sophisticated exploration strategies. Example, in robotic controlled tasks, continuous action spaces demand exploration strategies that efficiently navigate the high dimensional space. By delving into deep reinforcement learning, multi-agent scenarios, and transfer learning, you will gain insights into handling more complex tasks, navigating interactions among multiple entities, and leveraging knowledge across different learning situations. These advanced topics represent the cutting edge of RL research and application, pushing the boundaries of what can be achieved in artificial intelligence. Hands-on projects, card poll with Q-learning. Description: implement Q-learning to control a card poll system using OpenAI Gym. This classic RL problem involves balancing a poll on a moving cart. Objective: develop a Q-learning agent to learn optimal actions for balancing the poll over time. Lunar lander with deep Q network, DQN. Description: utilize DQN to train an agent for the lunar lander environment in OpenAI Gym. The agent must learn to land a spacecraft safely on the moon. Objective: apply deep reinforcement learning to handle more complex state, spaces, and continuous actions. Experiment and iterate. Hyperparameter tuning approach. Systematically vary hyperparameters such as learning rates, discount factors, and exploration rates. Objective: observe how changes in hyperparameters impact the learning process and final performance of the RL agent. Algorithm switching approach. Experiment with different RL algorithms, that is Q-learning, DQN, policy gradient, on the same problem. Objective: compare the strengths and weaknesses of each algorithm in terms of convergence, speed, and final performance. Diverse environments approach. Apply RL algorithms to a variety of environments within OpenAI Gym, ranging from classic controlled tasks to robotic simulations. Objective: gain experience adapting RL techniques to different problems domains and understand their generalizability. Transfer learning scenarios. Approach. Explore transfer learning by training an agent on one environment and evaluating its performance on a related but different environment. Objective. Assess the extent to which knowledge gained in one task can benefit learning in a new similar task. Real world inspired challenges. Approach. Design RL projects inspired by real world challenges such as traffic flow optimization, financial portfolio management, or robotic manipulation tasks. Objective. Apply RL concepts to address problems with practical implications, fostering a deeper understanding of real world applications. Additional guidance, documentation and visualization. Recommendation. Keep detailed documentation of your experiments, including changes made, results observed, and insights gained. Objective. Enhance your ability to analyze and understand the impact of different choices during the implementation process. Collaborate and seek feedback. Recommendation. Share your projects and findings with the RL community, seeking feedback and insights. Objective. Gain diverse perspectives, uncover potential pitfalls, and accelerate your learning through collaboration. By engaging in hands-on projects, experimenting with various algorithms and parameters, and tackling diverse environments, you will solidify your understanding of reinforcement learning and develop practical skills. The iterative nature of experimentation is key to mastering RL, as it allows you to refine your approach based on empirical results and challenges encountered during implementation. Reinforcement learning and machine learning. Reinforcement learning RL and machine learning ML are intertwined, and their collaboration offers a comprehensive approach to solving complex problems. Here is a scenario illustrating how reinforcement learning collaborates with machine learning. Scenario. Autonomous drone delivery. Problem definition. Objective. Design an autonomous drone delivery system to optimize package delivery routes in a city. Machine learning involvement. Machine learning is used to analyze historical data considering factors like traffic patterns, weather conditions, and delivery times. Clustering algorithms identify areas with high demand and potential obstacles. State representation. Objective. Represent the environment and possible drone actions. Reinforcement learning involvement. Reinforcement learning defines the state space, including variables like drone location, package status, and traffic conditions. The actions involve deciding which route to take and when to deliver a package. Initial policy learning. Objective. Train the drone to make informed decisions. Reinforcement learning involvement. An initial reinforcement learning model, perhaps using Q-learning or a deep reinforcement learning approach, is trained in a simulated environment. The drone learns to associate states with actions that maximize cumulative rewards, considering factors like delivery speed and fuel efficiency. Continuous learning from experience. Objective. Enable the system to adapt to changing conditions. Reinforcement learning involvement. The drone continually interacts with the environment, learning from real-world deliveries. The reinforcement learning model is updated with new experiences, allowing it to adapt to evolving traffic patterns, road closures, and other dynamic factors. Transfer learning for new cities. Objective. Expand the drone delivery system to new cities. Reinforcement learning involvement. Transfer learning techniques are employed. The RL model pre-trained in one city is adapted to a new city by leveraging the knowledge gained. This accelerates learning in the new environment, considering similarities and differences in city layouts and traffic conditions. Collaboration with supervised learning objective, enhance decision making with predictive models, machine learning involvement. Supervised learning models are used to predict future traffic conditions, weather changes, or demand spikes. These predictions serve as inputs to the RL model, aiding the drone in making more informed decisions. Monitoring and anomaly detection objective, ensure robust and safe operation. Machine learning involvement, machine learning algorithms monitor the drone's performance and detect anomalies. Anomaly detection models trained on historical data identify irregularities in the drone's behavior, signaling potential issues that trigger revolution of the RL policies. Human in the loop learning objective, incorporate human feedback for improved decision making. Reinforcement learning involvement. A human in the loop system allows human operators to provide feedback on the reinforcement learning decisions. This feedback is used to refine the reinforcement learning model, addressing situations where the model may struggle or encounter unexpected challenges. In this scenario, reinforcement learning collaborates with machine learning at various stages, from initial policy learning and continuous adaptation to transfer learning for scalability and integration with predictive models. This collaboration creates a dynamic and adaptive autonomous drone delivery system that learns from experience, adjusts to new environments, and leverages machine learning insights for improved decision making. Reinforcement learning and neural network. Reinforcement learning collaborates extensively with neural networks, especially in scenarios where complex decision making and pattern recognition are required. Here is a comprehensive overview of how reinforcement learning collaborates with neural networks. Representation of policies and value functions. Reinforcement learning involvement. RL often involves the representation of policies and value functions. Neural network collaboration. Neural networks are employed to represent these policies and value functions, allowing for the approximation of complex decision-making strategies. Deep reinforcement learning. Reinforcement learning involvement in tasks with high-dimensional state spaces of continuous action spaces. Traditional RL approaches may struggle. Neural network collaboration. DRL combines RL with deep neural networks known as deep Q networks (DQN) or policy gradient methods, enabling efficient learning from raw sensory input and handling more complex scenarios. Q learning with neural networks. Reinforcement learning involvement. Q learning is a classical RL algorithm that learns action values for state action pairs. Neural network collaboration. Instead of maintaining a table of Q values, a neural network is used to approximate the Q function, allowing the model to generalize across similar state action pairs. Policy gradient methods. Reinforcement learning involvement. Policy gradient methods directly optimize policies to maximize expected rewards. Neural network collaboration. Neural networks are employed as policy approximators, mapping state to actions. Training involves adjusting the neural network's parameters to increase the likelihood of good actions. Actor-critic architectures. Reinforcement learning involvement. Actor-critic methods combine value-based and policy-based approaches. Neural network collaboration. The actor, policy, and critic, value function, are represented by separate neural networks. The actor suggests actions, and the critic evaluates their goodness. This dual network structure enhances stability and learning efficiency. Experience replay. Reinforcement learning involvement. Experience replay is a technique that helps stabilize learning by storing and randomly sampling past experiences. Neural network collaboration. A replay buffer holds tuples of State, action, reward, next state, which are sampled during training. Neural networks are trained on batches of these experiences, contributing to more stable and efficient learning. Continuous control with neural networks, reinforcement learning involvement. Traditional RL algorithms like DQN may struggle with continuous action spaces, neural network collaboration. Neural networks, particularly in policy gradient methods and actor critic architectures, excel in handling continuous action spaces, enabling RL applications in robotics and control systems. Transfer learning in neural networks. Reinforcement learning involvement. Transfer learning involves leveraging knowledge gained in one task to improve performance in another. Neural network collaboration. Pre-trained neural networks used as feature extractors can be fine-tuned for new tasks in reinforcement learning. This accelerates learning and promotes better generalization. Curriculum learning, reinforcement learning involvement. Curriculum learning involves gradually increasing the complexity of tasks during training. Neural network collaboration. Neural networks adapt to changing task complexities, allowing RL agents to learn progressively more challenging behaviors over time. Interactions with real world data. Reinforcement learning involvement. Reinforcement learning often interacts with real world data, making it imperative to adapt to dynamic environments. Neural network collaboration. Neural networks facilitate this adaptability by learning from diverse and dynamic data sources, allowing RL agents to generalize well in the face of uncertainties. Human feedback and imitation learning, reinforcement learning involvement. Human feedback is valuable for refining RL policies. Neural network collaboration. Neural networks, especially in imitation learning scenarios, help the RL agent mimic expert behaviors based on human demonstrations, contributing to faster and safer learning. Explainability and interpretability. Reinforcement learning involvement. In critical applications, understanding and explaining RL decisions are essential. Neural network collaboration. Techniques like attention mechanisms in neural networks provide insights into decision-making processes, enhancing the interpretability of reinforcement learning models. Safety and ethical considerations, reinforcement learning involvement. Ensuring the safety and ethical use of RL models is a growing concern. Neural network collaboration. Neural networks contribute to designing safer RL systems by incorporating safety constraints and ethical considerations into the learning process. In summary, the collaboration between reinforcement learning and neural networks is foundational to addressing the challenges of complex decision making in dynamic environments. Neural networks serve as powerful function approximators, enabling RL models to learn and generalize from diverse data sources, handle continuous action spaces, and adapt to real world complexities. This synergy is at the forefront of advancements in artificial intelligence, pushing the boundaries of what RL systems can achieve. Reinforcement learning and deep learning. Reinforcement learning and deep learning often collaborate to address complex problems that involve high dimensional data and intricate decision making. Here is a comprehensive overview of how reinforcement learning collaborates with deep learning. Deep neural networks for function approximation. Reinforcement learning involvement. Reinforcement learning often requires approximating complex functions such as state action values or policies. Deep learning collaboration. Deep neural networks, with their ability to approximate complex functions, are employed to represent these functions in RL models. This collaboration is commonly known as deep reinforcement learning (DRL). Deep networks, DQN, reinforcement learning involvement. DQN is a classical algorithm in reinforcement learning used to approximate the Q function for discrete action spaces. Deep learning collaboration. DQN leverages deep neural networks to efficiently approximate the Q function, allowing RL agents to handle high-dimensional state spaces and learn optimal policies. Policy gradient methods with neural networks. Reinforcement learning involvement. Policy gradient methods directly optimize policies to maximize expected rewards. Deep learning collaboration. Neural networks serve as policy approximators, mapping states to actions. Training involves adjusting the neural network's parameters to increase the likelihood of good actions. Actor-critic architectures. Reinforcement learning involvement. Actor-critic methods combine value-based critic and policy-based actor approaches. Deep learning collaboration. The actor, policy, and critic value function are represented by separate deep neural networks. The actor suggests actions and the critic evaluates their goodness. This dual network structure enhances stability and learning efficiency. Deep deterministic policy gradients, DDPG. Reinforcement learning involvement. DDPG is an algorithm designed for continuous action spaces. Deep learning collaboration. DDPG employs deep neural networks for both the actor and critic components, enabling reinforcement learning agents to handle problems with continuous action spaces effectively. Continuous control with deep deterministic policy gradients, TD3. Reinforcement learning involvement. TD3 is an extension of DDPG that addresses certain challenges. Deep learning collaboration. TD3 utilizes deep neural networks to approximate the Q function and policy, providing more stable learning in continuous control tasks. Experience replay with neural networks. Reinforcement learning involvement. Experience replay is a technique to store and reuse past experiences for more stable learning. Deep learning collaboration. Deep neural networks are used to approximate the Q function, and experience replay enables the training of reinforcement learning agents with batches of diverse and previously encountered experiences. Transfer learning with deep learning. Reinforcement learning involvement. Transfer learning involves leveraging knowledge from one task to improve performance in another. Deep learning collaboration. Pre-trained deep neural networks can be used as feature extractors in reinforcement learning, allowing the agent to transfer learned features from one task to another, accelerating the learning process. Curriculum learning with deep networks. Reinforcement learning involvement. Curriculum learning involves gradually increasing the complexity of tasks during training. Deep learning collaboration. Neural networks adapt to changing task complexities, allowing RL agents to learn progressively more challenging behaviors over time. Policy distillation. Reinforcement learning involvement. Policy distillation involves transferring knowledge from a training policy to a new policy. Deep learning collaboration. Deep neural networks play a crucial role in representing policies, and policy distillation leverages these networks to transfer learned policies to new RL agents, incorporating deep learning in model-based RL. Reinforcement learning involvement. Model-based RL involves learning a model of the environment to plan and make decisions. Deep learning collaboration. Deep neural networks can be employed to represent the learned model, allowing for more accurate and flexible predictions of the environment dynamics. Neural architecture search, NAS, in reinforcement learning. Reinforcement learning involvement. Enhancing reinforcement learning model architectures is crucial for better performance. Deep learning collaboration. NAS techniques, which use RL principles to search for optimal neural network architectures, contribute to improving the performance of reinforcement learning models. Hyperparameter optimization with deep learning. Reinforcement learning involvement. Efficient hyperparameter tuning is essential for improving reinforcement learning performance. Deep learning collaboration. Deep learning techniques such as Bayesian optimization or reinforcement learning for hyperparameter tuning can be employed to find optimal settings for neural networks architectures in reinforcement learning. Adversarial training for robustness. Reinforcement learning involvement. Ensuring robustness is crucial for reinforcement learning models in dynamic environments. Deep learning collaboration. Adversarial training, commonly used in deep learning, can be applied to reinforcement learning models to enhance their robustness against perturbations and unexpected scenarios. Interactions with real-world data. Reinforcement learning involvement. Reinforcement learning often interacts with real-world data, making it imperative to adapt to dynamic environments. Deep learning collaboration. Deep learning models facilitate adaptability by learning from diverse and dynamic data sources, allowing reinforcement learning agents to generalize well in the face of uncertainties. Interpretability and explainability. Reinforcement learning involvement. Understanding and explaining RL decisions are essential in certain applications. Deep learning collaboration. Techniques such as attention mechanisms in deep neural networks provide insights into decision-making processes, enhancing the interpretability of reinforcement learning models. In essence, the collaboration between reinforcement learning and deep learning is foundational for addressing challenges in dynamic and complex environments. Deep neural networks serve as powerful function approximators, enabling reinforcement learning agents to learn from high-dimensional data, generalize across diverse scenarios, and make sophisticated decisions. This collaboration, often referred to as deep reinforcement learning, represents a leading edge approach in artificial intelligence, allowing for the development of intelligent agents capable of tackling real world problems. Reinforcement learning and natural language processing. Reinforcement learning and natural language processing collaborate to solve various complex problems involving language understanding, generation, and interaction. Here is a comprehensive overview of how reinforcement learning collaborates with NLP. Dialogue systems and chatbots. Reinforcement learning involvement. In interactive applications, RL is used to train agents that engage in conversations. NLP collaboration. NLP techniques such as natural language understanding and generation are combined with RL to create dialogue systems and chatbots that can learn from user interactions over time to improve responses. Text summarization. Reinforcement learning involvement. Summarizing long pieces of text is a complex task that reinforcement learning can be applied to. NLP collaboration. NLP methods for understanding document structures and extracting important information are combined with RL to train summarization models that capture key content. Language generation in RL. Reinforcement learning involvement. Language generation tasks involve creating coherent and contextually relevant sentences. NLP collaboration. NLP techniques for language modeling and syntax understanding are integrated with RL to train models that generate natural and contextually appropriate language. Machine translation. Reinforcement learning involvement. Translating languages involves making decisions based on context and semantics. NLP collaboration. NLP methods for language understanding and translation combined with RL help train models that improve translation quality over the based on user feedback. Named entity recognition. NER. Reinforcement learning involvement, identifying entities, names, locations, etc. in text is a sequential decision-making problem. NLP collaboration, NLP techniques for named entity recognition coupled with RL enable models to make decisions about entity boundaries in context, improving accuracy. Text-based games and reinforcement learning. Reinforcement learning involvement. RL is applied to text-based games where the agent interacts with the environment through natural language commands. NLP collaboration. NLP methods are crucial for understanding and generating text-based responses in the game environment, creating a more immersive and interactive experience. Sentiment analysis and reinforcement learning. Reinforcement learning involvement. Sentiment analysis involves understanding the sentiment expressed in text. NLP collaboration. NLP techniques for sentiment analysis combined with reinforcement learning enable models to learn from user feedback to better understand and interpret sentiments over time. Interactive learning from demonstrations. Reinforcement learning involvement. Learning from demonstrations involves training agents based on expert behavior. NLP collaboration. NLP models can generate demonstration data or assist in understanding and interpreting expert behavior in text-based demonstrations. Dialogue policy learning. Reinforcement learning involvement. In conversational agents, reinforcement learning is used to learn optimal dialogue policies. NLP collaboration. NLP techniques help in extracting features from conversational data, enabling RL models to learn effective dialogue strategies. Conversational artificial intelligence and personalization. Reinforcement learning involvement. RL helps in personalizing responses in conversational artificial intelligence. NLP collaboration. NLP models analyze user preferences, intents, and context to provide personalized responses, enhancing user engagement. Multi-turn conversations and context handling. Reinforcement learning involvement. Multi-turn conversations require handling context across multiple interactions. NLP collaboration. NLP methods for context management and understanding long-term dependencies in conversations are combined with RL to improve the continuity and coherence of responses. Text-based question answering. Reinforcement learning involvement. Answering questions from text involves making sequential decisions. NLP collaboration. NLP models for question answering are integrated with RL to train agents that can dynamically retrieve and present information in response to user queries. Active learning for annotation. Reinforcement learning involvement. Active learning involves selecting the most informative data for annotation. NLP collaboration. NLP models, particularly those capable of uncertainty estimation, contribute to the active learning process, guiding the RL agent to request annotations for the most ambiguous or informative examples. Human in the loop training. Reinforcement learning involvement. In certain NLP applications, human feedback is crucial for refining models. NLP collaboration. NLP models facilitate human in the loop training, allowing users to provide feedback on generated text or correct mistakes, which is then used to update RL policies. Ethical considerations in language generation. Reinforcement learning involvement. Ethical concerns such as biased language generation need to be addressed in RL models. NLP collaboration. NLP models are used to identify and mitigate biases in language generation, ensuring more ethical and inclusive text generation. Cross-lingual understanding and generation. Reinforcement learning involvement. Cross-lingual applications involve understanding and generating content in multiple languages. NLP collaboration. NLP models for cross-lingual understanding and generation work hand in hand with RL to create agents that can operate effectively across different language contexts. In summary, the collaboration between reinforcement learning and natural language processing is instrumental in addressing the challenges posed by language related tasks. Reinforcement learning provides a framework for learning optimal decision making policies. Fuzzy logic. Reinforcement learning and fuzzy logic collaborate in various applications to address complex decision making problems that involve uncertainty and imprecision. Here is a comprehensive overview of how RL collaborates with fuzzy logic. Uncertainty handling. Reinforcement learning involvement. RL deals with uncertain environments where outcomes are not deterministic. Fuzzy logic collaboration. Fuzzy logic is well suited for handling uncertainty by allowing for the representation of vague or imprecise information through linguistic terms and fuzzy sets. Membership functions in state and action representation. Reinforcement learning involvement. State and action representation in RL are crucial for decision making. Fuzzy logic collaboration. Fuzzy logic is employed in RL to define membership functions that represent the degree to which a state or action belongs to a particular category, capturing the imprecision inherent in these representations. Fuzzy Q learning. Reinforcement learning involvement. Q learning is a fundamental RL algorithm for estimating the quality of actions. Fuzzy logic collaboration. Fuzzy Q learning extends traditional Q learning by incorporating fuzzy logic to handle imprecise state and action representations, allowing for a more flexible and adaptive approach. Fuzzy inference systems in policy decisions. Reinforcement learning involvement. RL agents make decisions based on learned policies. Fuzzy logic collaboration. Fuzzy inference systems FIS are integrated into RL to make policy decisions considering fuzzy input-output relationships, especially useful when dealing with subjective or ambiguous criteria. Adaptive fuzzy systems for dynamic environments. Reinforcement learning involvement. RL systems must adapt to changing environments. Fuzzy logic collaboration. Adaptive fuzzy systems integrated with RL allow for the dynamic adjustment of fuzzy rules and membership functions, enabling RL agents to adapt to evolving conditions. Fuzzy controllers in action selection. Reinforcement learning involvement. RL agents select actions based on learned policies. Fuzzy logic collaboration. Fuzzy controllers are applied in RL to determine the appropriate actions to take considering fuzzy input conditions and rules that capture imprecise decision criteria. Fuzzy reward modeling. Reinforcement learning involvement. Rewards guide the learning process in RL. Fuzzy logic collaboration. Fuzzy reward modeling allows for the representation of rewards in a more nuanced way, considering degrees of satisfaction or dissatisfaction rather than binary outcomes. Fuzzy state transitions. Reinforcement learning involvement. RL involves transitioning between states based on actions. Fuzzy logic collaboration. Fuzzy logic can be employed to model the uncertainty associated with state transitions, especially in situations where the transitions are not precisely defined. Fuzzy rule-based system for policy optimization. Reinforcement learning involvement. RL aims to optimize policies for decision making. Fuzzy logic collaboration. Fuzzy rule-based systems contribute to RL by providing a rule-driven approach for policy optimization, considering imprecise input conditions and actions. Fuzzy clustering for state space partitioning. Reinforcement learning involvement. Efficient representation of the state space is crucial for RL. Fuzzy logic collaboration. Fuzzy clustering techniques are applied to partition the state space into fuzzy regions, allowing for a more adaptive and flexible representation in RL. Fuzzy reinforcement learning in multi-agent systems. Reinforcement learning involvement. RL principles extend to multi-agent scenarios. Fuzzy logic collaboration. Fuzzy reinforcement learning is employed in multi-agent systems to handle complex interactions and imprecise communication between agents, enhancing coordination. Fuzzy logic for explainability. Reinforcement learning involvement. Understanding RL decisions is crucial for transparency and trust. Fuzzy logic collaboration. Fuzzy logic contributes to explainability by providing a more interpretable representation of decision criteria and capturing the uncertainty associated with certain decisions made by RL agents. Fuzzy sets in reward shaping. Reinforcement learning involvement. Reward shaping is used to guide RL agents toward desirable behaviors. Fuzzy logic collaboration. Fuzzy sets are employed in reward shaping to represent the gradual satisfaction or dissatisfaction associated with the different states or actions, allowing for a more nuanced shaping process. Hybrid fuzzy RL systems. Reinforcement learning involvement. RL systems seek to learn optimal policies for decision making. Fuzzy logic collaboration. Hybrid systems combine RL and fuzzy logic, leveraging the strengths of each paradigm to create more robust and adaptive decision-making systems. Fuzzy cognitive maps in decision support. Reinforcement learning involvement. RL agents make decisions based on learned policies. Fuzzy logic collaboration. Fuzzy cognitive maps, FCMS, are integrated into RL for decision support, allowing for a more human-like reasoning process by capturing the imprecision and vagueness in decision criteria. Fuzzy logic in fallback mechanisms. Reinforcement learning involvement. RL systems often need fallback mechanisms for handling unforeseen situations. Fuzzy logic collaboration. Fuzzy logic is applied to design fallback strategies considering fuzzy rules for determining alternative actions or policies where RL agents encounter uncertain or unanticipated scenarios. In summary, the collaboration between reinforcement learning and fuzzy logic provides a powerful framework for addressing uncertainty, imprecision, and adaptability in decision-making systems. Fuzzy logic complements RL by offering a flexible and interpretable way to represent and reason about uncertain information, enhancing the robustness and adaptability of RL agents in various applications. Decision trees. Reinforcement learning and decision trees collaborate in various applications to address complex decision-making problems. Decision trees, known for their interpretability and ability to handle categorical and numerical data, can be integrated with RL to enhance decision strategies. Here is a comprehensive overview of how RL collaborates with decision trees. State and action representation. Reinforcement learning involvement. RL involves representing the state and action spaces for decision making. Decision tree collaboration. Decision tree can be employed to discretize or categorize continuous state and action spaces, facilitating their representation in RL models. Policy improvement using decision trees. Reinforcement learning involvement. RL agents aim to learn optimal policies through trial and error. Decision tree collaboration. Decision trees are utilized to analyze and improve RL policies by identifying critical features and conditions that lead to favorable or unfavorable outcomes. Exploration strategies. Reinforcement learning involvement. RL involves balancing exploration, trying new actions, and exploitation, choosing non-good actions. Decision tree collaboration. Decision trees can assist in guiding exploration strategies by providing insights into the potential value of unexplored actions based on historical data. State action value estimation. Reinforcement learning involvement. RL often estimates the value of state action pairs to guide decision making. Decision tree collaboration. Decision tree can be used to approximate the state action values, especially in discrete action spaces, aiding RL models in value estimation. Interpretable action selection. Reinforcement learning involvement. RL agents need to select actions based on learned policies. Decision tree collaboration. Decision trees contribute to interpretable action selection by providing clear decision rules based on observed state features. Policy enforcement with decision trees. Reinforcement learning involvement. RL models aim to enforce policies that maximize cumulative rewards. Decision tree collaboration. Decision trees can help enforce policies by providing guidelines on which actions to take in specific states, aligning with the learned RL policies. Action pruning and selection. Reinforcement learning involvement. RL agents may need to prune or select actions based on their potential impact. Decision tree collaboration. Decision trees aid RL models in action pruning by highlighting features that are influential in determining the best course of action in a given state. Feature importance analysis. Reinforcement learning involvement. Understanding the importance of features is crucial for informed decision making. Decision tree collaboration. Decision trees help in analyzing feature importance, guiding RL agents to focus on the most relevant aspects of the environment. Ensemble methods with decision trees. Reinforcement learning involvement. RL models can benefit from ensemble methods for improved stability. Decision tree collaboration. Decision tree can be part of ensemble methods such as random forests to enhance the robustness and generalization of RL models. Dynamic decision rules. Reinforcement learning involvement. RL models often need to adapt to changing environments. Decision tree collaboration. Decision tree, particularly when used in online learning settings, allow RL models to dynamically update decision rules based on new data and evolving conditions. Hierarchical decision making. Reinforcement learning involvement. Hierarchical RL involves organizing decisions into multiple levels. Decision tree collaboration. Decision trees can be used to represent hierarchical decision-making structures, aiding RL agents in navigating complex environments with multiple levels of abstraction. Reward shaping with decision trees. Reinforcement learning involvement. Reward shaping is used to guide RL agents toward desirable behaviors. Decision tree collaboration. Decision trees contribute to reward shaping by identifying states and actions that lead to positive or negative outcomes, helping RL agents understanding the impact of their choices. Policy adaptation. Reinforcement learning involvement. RL models may need to adapt their policies over time. Decision tree collaboration. Decision trees assist in policy adaptation by providing insight into the changing importance of features and conditions, allowing RL agents to adjust their strategies accordingly. Incorporating domain knowledge. Reinforcement learning involvement. Domain knowledge can enhance decision making in RL. Decision tree collaboration. Decision trees allow the incorporation of domain knowledge through explicit rules, enabling RL agents to benefit from expert insights and heuristics. Human in the loop decision trees. Reinforcement learning involvement. Incorporating human feedback is valuable for refining RL policies. Decision tree collaboration. Decision trees can be part of a human in the loop system, allowing human to provide explicit decision rules and feedback, influencing the RL decision making process. Explainability and transparency. Reinforcement learning involvement, understanding, and explaining RL decisions is essential for trust. Decision tree collaboration. Decision trees offer transparency and explainability by providing explicit decision rules, making it easier to interpret how reinforcement learning models arrive at specific decisions. In summary, the collaboration between reinforcement learning and decision trees is advantageous for creating interpretable and adaptive decision making systems. Decision trees enhance the transparency of reinforcement learning models, guide exploration and exploitation strategies, and provide insights into the importance of different features and actions, making them valuable components in various reinforcement learning applications. Reinforcement learning and sport vector machines can collaborate to address various challenges in decision making, classification, and function approximation. Here is a comprehensive overview of how reinforcement learning collaborates with SVM. State and action representation. Reinforcement learning involvement. Reinforcement learning involves representing states and actions for decision making. SVM collaboration. SVMs can be utilized to pre-process and transform state and action representations, particularly in cases where linear separation or dimensionality reduction is beneficial. Function approximation in reinforcement learning. Reinforcement learning involvement. RL often requires approximating value functions or policies. SVM collaboration. SVMs can be used for function approximation in reinforcement learning, providing a different approach compared to traditional methods like neural networks. SVMs for policy evaluation. Reinforcement learning involvement. Policy evaluation is a crucial step in reinforcement learning to estimate the value of different states. SVM collaboration. SVMs can be employed to approximate the value function in policy evaluation tasks, offering a different perspective compared to traditional reinforcement learning methods. SVMs in imitation learning. Reinforcement learning involvement. Imitation learning involves learning from expert demonstrations. SVM collaboration. SVMs can be used to model the decision boundary between expert and non-expert actions, aiding reinforcement learning agents in imitating desired behaviors. Sport vector regression (SVR) in reinforcement learning. Reinforcement learning involvement. Reinforcement learning often requires estimating continuous state or action values. SVM collaboration. SVR can be applied to estimate continuous value functions in RL, providing an alternative to traditional regression techniques. Classification with SVMs in RL. Reinforcement learning involvement. RL models may involve classification tasks such as identifying optimal actions. SVM collaboration. SVMs can be used for classification tasks within reinforcement learning, offering a robust and effective approach to decision boundary estimation. SVMs for state space partitioning. Reinforcement learning involvement. Efficient state space partitioning is crucial in reinforcement learning. SVM collaboration. SVMs can assist in state space partitioning by providing a clear decision boundary between different regions, aiding in the representation of complex environments. Policy improvement with SVMs. Reinforcement learning involvement. Reinforcement learning agents aim to improve policies over time. SVM collaboration. SVMs can be used to analyze and improve reinforcement learning policies by identifying critical features and decision boundaries that influence that policy. SVM ensemble in RL. Reinforcement learning involvement. Ensembles improve the stability of reinforcement learning models. SVM collaboration SVM ensembles where multiple SVMs are combined can be applied in reinforcement learning for enhanced robustness and generalization. Hybrid RL SVM systems, reinforcement learning involvement. RL models seek to learn optimal policies. SVM collaboration, hybrid systems combining RL and SVMS leverages the strengths of both approaches, offering flexibility and interpretability. Kernel tricks for non-linearity. Reinforcement learning involvement. RL models may need to handle non-linear relationships in the data. SVM collaboration. SVMs with kernel tricks such as radial basis function RBF kernels can be applied to capture non-linear relationships in RL tasks. SVMs for feature selection, reinforcement learning involvement. Feature selection is essential for efficient reinforcement learning. SVM collaboration. SVMs can be used for feature selection, identifying the most relevant features that influence decision making in reinforcement learning. SVMs for anomaly detection, reinforcement learning involvement. RL agents may need to detect anomalies in the environment. SVM collaboration. SVMs excel in anomaly detection and can be applied in reinforcement learning to identify unexpected or unusual states. Online learning with SVMs, reinforcement learning involvement. Online learning is crucial for RL in dynamic environments. SVM collaboration. SVMs, particularly in online learning settings, can adapt to changing conditions and new data, making them suitable for dynamic RL scenarios. SVMs in batch learning for policy evaluation. Reinforcement learning involvement. Policy evaluation involves estimating the value of different states in reinforcement learning. SVM collaboration. SVMs, especially in batch learning scenarios, can be employed for accurate and stable policy evaluation. Explainability and transparency. Reinforcement learning involvement, understanding and explaining RL decisions is essential. SVM collaboration. SVMs with their clear decision boundaries and support vectors contribute to the explainability and transparency of RL models. In summary, the collaboration between reinforcement learning and support vector machines provides a versatile framework for addressing various challenges in decision making and function approximation. SVMs offer different perspectives on policy evaluation, function approximation, and decision boundary estimation, making them valuable components in the toolkit of reinforcement learning practitioners. Reinforcement learning and clustering collaborate in various applications to address complex decision-making problems and representational challenges. Clustering techniques which group similar data points together can be integrated with RL to enhance state representation, facilitate exploration strategies, and improve decision making. Here is a comprehensive overview of how reinforcement learning collaborates with clustering. State representation through clustering. Reinforcement learning involvement. RL involves representing states for decision making clustering collaboration. Clustering techniques such as k-means can be employed to group similar states together, creating a more compact and representative state space for reinforcement learning models. Hierarchical state representations, reinforcement learning involvement. Reinforcement learning often benefits from hierarchical representations of states. Clustering collaboration, hierarchical clustering methods contribute to organizing states into meaningful levels of abstraction, assisting reinforcement learning agents in decision making at different levels of granularity. Feature learning via clustering. Reinforcement learning involvement. RL models may need to extract meaningful features from high dimensional observations. Clustering collaboration. Clustering can serve as a feature learning mechanism, allowing RL agents to focus on the relevant aspects of the environment by grouping similar features together. State space partitioning, reinforcement learning involvement. Efficient partitioning of the state space is crucial for reinforcement learning. Clustering collaboration. Clustering methods contribute to state space partitioning by identifying regions with similar dynamics, aiding RL models in capturing the underlying structure of the environment, reducing dimensionality. Reinforcement learning involvement. RL often encounters high dimensional state spaces. Clustering collaboration. Clustering can be used as a dimensionality reduction technique, grouping similar dimensions together and simplifying the representation of states for reinforcement learning models. Novelty detection through clustering. Reinforcement learning involvement. RL agents may encounter novel or unseen states. Clustering collaboration. Clustering techniques can help detect novel states by identifying patterns that deviate from the learned clusters, aiding RL models in handling unexpected scenarios. Adaptive exploration with clustering. Reinforcement learning involvement. Reinforcement learning involves balancing exploration and exploitation. Clustering collaboration. Clustering information can guide exploration strategies by identifying unexplored regions of the state space, allowing reinforcement learning agents to focus on areas with potential new insights. State abstraction for generalization. Reinforcement learning involvement. Generalization across similar states is crucial in reinforcement learning. Clustering collaboration. Clustering provides a natural way to abstract similar states, enabling reinforcement learning agents to generalize their knowledge to entire clusters rather than individual data points. Clustering for curriculum learning. Reinforcement learning involvement. Curriculum learning involves gradually increasing the complexity of tasks during training. Clustering collaboration. Clustering can be used in curriculum learning scenarios by organizing tasks into clusters based on their difficulty levels, allowing RL agents to learn progressively more challenging behaviors. Clustering for state similarity matrix. Reinforcement learning involvement. Defining similarity matrix is essential for RL, especially in model-based approaches. Clustering collaboration. Clustering can aid in defining state similarity matrix by grouping states based on their dynamics, assisting RL models in planning and decision making. Dynamically updating clusters. Reinforcement learning involvement. RL models need to adapt to changing environments. Clustering collaboration. Dynamically updating clusters allows RL models to adjust to evolving conditions, ensuring that the clustering representation remains relevant over time. Reward shaping based on clusters. Reinforcement learning involvement. Reward shaping guides RL agents toward desirable behaviors. Clustering collaboration. Clustering can contribute to reward shaping by providing bases for defining rewards that are specific to different state clusters, promoting desired behavior within each group. Incorporating temporal information. Reinforcement learning involvement. Temporal information is crucial for sequential decision making. Clustering collaboration. Clustering, when combined with temporal information, enables RL models to capture both spatial and temporal dependencies in the state space, enhancing the representation of dynamic environments. Human in the loop clustering. Reinforcement learning involvement. Incorporating human insights is valuable for refining RL models. Clustering collaboration. Clustering can be part of a human in the loop system, allowing humans to guide the clustering process and provide insights into meaningful state groupings. Ensemble clustering for model robustness. Reinforcement learning involvement. model robustness is crucial for RL. Clustering collaboration. Ensemble. Clustering methods can enhance the robustness of RL models by combining multiple clustering solutions, providing stability in state representation. In summary, the collaboration between reinforcement learning and clustering techniques offers a powerful approach to handling state representation, exploration, and decision-making challenges. Clustering provides a structured way to organize and simplify the state space, facilitating more effective. Reinforcement learning and data mining collaborate in various ways to extract valuable insights, discover patterns, and improve decision making. Here is a comprehensive overview of how reinforcement learning collaborates with data mining. Knowledge discovery from data. Reinforcement learning involvement. RL aims to discover optimal strategies through interactions with an environment. Data mining collaboration. Data mining techniques help in the initial exploration of data, identifying patterns, trends, and potential areas of interest for reinforcement learning. Feature selection and engineering. Reinforcement learning involvement. Efficient feature representation is crucial for reinforcement learning. Data mining collaboration. Data mining methods, including feature selection and engineering, contribute to preparing meaningful and relevant features for reinforcement learning models, improving their effectiveness. Pre-processing for state representation. Reinforcement learning involvement. Reinforcement learning involves representing states for decision making. Data mining collaboration. Data mining pre-processing techniques such as normalization or scaling help in preparing state representations, ensuring that reinforcement learning models work with standardized and meaningful input. Pattern recognition and anomaly detection. Reinforcement learning involvement. Reinforcement learning agents may need to recognize patterns or detect anomalies in the environment. Data mining collaboration. Data mining techniques, particularly pattern recognition and anomaly detection algorithms, assist reinforcement learning models in identifying regularities or unexpected events in the data. Data clustering for state grouping. Reinforcement learning involvement. Efficient state representation is crucial for reinforcement learning models. Data mining collaboration. Clustering methods in data mining help group similar states together, aiding reinforcement learning models in creating a more compact and manageable state space. Sequential pattern mining. Reinforcement learning involvement. Reinforcement learning often deals with sequential decision making. Data mining collaboration. Sequential pattern mining algorithms assist in identifying recurring sequences of events or actions in historical data, offering insights into the temporal dynamics that reinforcement learning models can leverage. Association rule mining for action sequences. Reinforcement learning involvement. Reinforcement learning agents learn sequences of actions for decision making. Data mining collaboration. Association rule mining identifies frequent patterns of co-occurring actions or events, aiding reinforcement learning models in understanding the relationships between different actions. Data sampling for model training. Reinforcement learning involvement. Training RL models may require careful data sampling. Data mining collaboration. Data mining techniques contribute to strategic data sampling, ensuring that reinforcement learning models are trained on representative and diverse samples, improving generalization, handling imbalanced data. Reinforcement learning involvement. Imbalanced data can pose challenges in training reinforcement learning models. Data mining collaboration. Data mining approaches such as resampling or weighting techniques address imbalanced datasets, contributing to the robustness of reinforcement learning models. Ensemble learning with RL and data mining models, reinforcement learning involvement, ensemble methods enhance the stability and performance of reinforcement learning models. Data mining collaboration, ensemble learning techniques, combining reinforcement learning and data mining models offer a synergistic approach to decision making, leveraging the strengths of both domains. Data fusion for improved state representation, reinforcement learning involvement, combining information from multiple sources can enhance state representation. Data mining collaboration, data fusion techniques integrate information from various data sources, contributing to a more comprehensive and informative state representation for reinforcement learning models. Predictive modeling for environment dynamics, reinforcement learning involvement. Understanding the dynamics of the environment is crucial for reinforcement learning. Data mining collaboration, predictive modeling techniques such as the series forecasting or regression help reinforcement learning models anticipate changes in the environment, improving decision making. Discovering relevant patterns for reward shaping. Reinforcement learning involvement. Reward shaping guides reinforcement learning agents toward desirable behaviors. Data mining collaboration. Identifying relevant patterns through association rule mining or pattern recognition assists in defining meaningful reward structures for reinforcement learning models. Human in the loop data mining, reinforcement learning involvement, incorporating human insights is valuable for refining reinforcement learning models. Data mining collaboration, human in the loop data mining allows experts to guide the data analysis process, providing domain knowledge that enhances the performance of both reinforcement learning and data mining models. Temporal data analysis for reinforcement learning policies. Reinforcement learning involvement. Temporal information is crucial for sequential decision making. Data mining collaboration. Analyzing temporal patterns in data supports reinforcement learning models in understanding the time dependent dynamics of the environment, improving policy formulation. Explainability and interpretability, reinforcement learning involvement, understanding and explaining reinforcement learning decisions is essential for trust. Data mining collaboration, data mining techniques contribute to explainability by providing interpretable patterns and insights, aiding in the transparent interpretation of reinforcement learning decisions. In summary, the collaboration between reinforcement learning and data mining provides a holistic approach to extracting knowledge, preparing data, and improving decision making complex environments. By leveraging the strengths of both domains, practitioners can create more robust and informed reinforcement learning models. Reinforcement learning and Bayesian networks collaborate to address uncertainty, model complex dependencies, and enhanced decision making. Bayesian networks, which represent probabilistic relationships between variables, can be integrated with reinforcement learning to provide a principled way to handle uncertainty and update beliefs about the environment. Here is a comprehensive overview of how reinforcement learning collaborates with Bayesian networks. Uncertainty modeling, reinforcement learning involvement. Reinforcement learning often deals with uncertain environments and outcomes. Bayesian networks collaboration. Bayesian networks excel at modeling uncertainty by representing probabilistic dependencies between variables. In reinforcement learning, they can be used to model uncertain state transitions, rewards, and observations. Probabilistic state representation, reinforcement learning involvement. Reinforcement learning involves representing states for decision making. Bayesian network collaboration. Bayesian networks provide a probabilistic representation of state variables, allowing RL models to capture the uncertainty associated with different states. Dynamic Bayesian networks for temporal dependencies, reinforcement learning involvement. Temporal dependencies are crucial for sequential decision making in reinforcement learning. Bayesian network collaboration. Dynamic Bayesian networks (DBNS) model temporal dependencies, enabling reinforcement learning models to reason about the evolution of the environment over time. Bayesian inference for belief update. Reinforcement learning involvement. Reinforcement learning agents often need to update their beliefs about their environment. Bayesian network collaboration. Bayesian inference allows reinforcement learning models to update their beliefs based on new information, making decisions that account for the most recent observations. State transition probabilities. Reinforcement learning involvement. Reinforcement learning models require accurate estimates of state transition probabilities. Bayesian network collaboration. Bayesian networks can model and update state transition probabilities based on observed data, contributing to more accurate reinforcement learning predictions. Reward distribution modeling, reinforcement learning involvement. Reinforcement learning agents learn from rewards, which can be uncertain or variable. Bayesian network collaboration. Bayesian networks assist in modeling the distribution of rewards, allowing reinforcement learning models to capture the uncertainty and variability associated with different outcomes. Policy optimization with Bayesian decision theory. Reinforcement learning involvement. Reinforcement learning agents optimize policies for decision making. Bayesian network collaboration. Bayesian network theory helps optimize policies by incorporating probabilistic information, allowing reinforcement learning agents to make decisions that balance exploration and exploitation effectively. Handling partial observations. Reinforcement learning involvement. RL agents often operate in environments with partial observations. Bayesian network collaboration. Bayesian network handle partial observations by providing a principled way to update beliefs and make predictions based on incomplete information. Bayesian reinforcement learning. Reinforcement learning involvement. Bayesian reinforcement learning combines Bayesian methods with reinforcement learning techniques. Bayesian network collaboration. Bayesian networks serve as a foundation for Bayesian reinforcement learning, allowing reinforcement learning models to reason about uncertainty, update beliefs, and make decisions under probabilistic conditions. Uncertainty aware exploration strategies. Reinforcement learning involvement. Balancing exploration and exploitation is a key challenge in RL. Bayesian network collaboration. Bayesian networks inform uncertainty aware exploration strategies, guiding RL agents to explore regions where the model is uncertain, potentially leading to new valuable information. Probabilistic policy representation. Reinforcement learning involvement. Policies guide RL agents' decision making. Bayesian network collaboration. Bayesian networks can represent probabilistic policies, allowing RL models to express uncertainty in decision-making strategies. Adaptive learning rates with Bayesian optimization. Reinforcement learning involvement. Adaptive learning rates can improve the efficiency of learning in RL. Bayesian network collaboration. Bayesian optimization, a technique related to Bayesian networks, can be used to adapt learning rates in RL models, optimizing the learning process, incorporating expert knowledge through Bayesian priors. Reinforcement learning involvement. Expert knowledge can enhance RL performance. Bayesian network collaboration. Bayesian priors within Bayesian networks allow RL models to incorporate expert knowledge, providing a structured way to blend human insights with data-driven learning. Bayesian models for transfer learning. Reinforcement learning involvement. Transfer learning enables RL models to leverage knowledge from one task in another. Bayesian network collaboration. Bayesian models facilitate transfer learning by capturing and updating the distribution of knowledge across tasks, enabling RL agents to generalize effectively. Hierarchical Bayesian models. Reinforcement learning involvement. Hierarchical RL involves organizing decisions into multiple levels. Bayesian network collaboration. Hierarchical Bayesian models offer a principled way to organize decision-making hierarchies, enabling RL models to reason about uncertainty and different levels of abstraction. Human in the loop Bayesian modeling. Reinforcement learning involvement. Incorporating human insights is valuable for refining RL models. Bayesian network collaboration. Human in the loop Bayesian modeling allows experts to guide the construction and updating of Bayesian networks, ensuring that domain knowledge is appropriately integrated into the RL decision-making process. In summary, the collaboration between reinforcement learning and Bayesian networks provides a powerful framework for handling uncertainty, updating beliefs, and making informed decisions in complex and dynamic environments. Bayesian networks offer a principled way to model probabilistic relationships, enhancing the capabilities of reinforcement learning agents in uncertain and partially observable scenarios. Reinforcement learning and evolutionary algorithms. Exploration and policy initialization. Reinforcement learning involvement. RL agents need to explore the environment to discover optimal policies. Evolutionary algorithm collaboration. Evolutionary algorithms can assist in exploration by generating diverse initial policies for RL agents, kickstarting the learning process. Policy search and optimization. Reinforcement learning involvement. RL involves searching for optimal policies through trial and error. Evolutionary algorithm collaboration. Evolutionary algorithms can be employed to search the policy space, evolving and optimizing policies over generations, especially useful in cases where traditional RL methods face challenges. Representation learning. Reinforcement learning involvement. Effective representation of state and action spaces is crucial in reinforcement learning. Evolutionary algorithm collaboration. Evolutionary algorithms contribute to representation learning by evolving compact and expressive representations for states, actions, or neural network architectures used in RL models. Hyperparameter tuning. Reinforcement learning involvement. Choosing appropriate hyperparameters is vital for RL performance. Evolutionary algorithm collaboration. Evolutionary algorithms can optimize hyperparameters such as learning rates or exploitation trade-offs to enhance the performance of RL algorithms. Population-based training. Reinforcement learning involvement. Training reinforcement learning models may require efficient exploration of the policy space. Evolutionary algorithm collaboration. Population-based training, a concept from evolutionary algorithms, involves maintaining a diverse set of policies. This can benefit reinforcement learning by prompting exploration and preventing premature convergence to suboptimal solutions. Transfer learning across tasks. Reinforcement learning involvement. Transfer learning enables reinforcement learning models to leverage knowledge from one task in another. Evolutionary algorithm collaboration. Evolutionary algorithm can facilitate transfer learning by evolving policies across a variety of related tasks, allowing reinforcement learning agents to generalize more effectively. Addressing multi-model environments. Reinforcement learning involvement. Reinforcement learning in multi-model environments involves handling diverse Types of data. Evolutionary algorithm collaboration. Evolutionary algorithm can evolve policies that effectively process and integrate information from different modalities, aiding reinforcement learning models in complex environments. Policy diversity, reinforcement learning involvement. Maintaining diversity in policies is important for exploration. Evolutionary algorithm collaboration. Evolutionary algorithms naturally generate diverse policies in their population, which can be advantageous in preventing RL models from converging to suboptimal solutions. Adaptive learning rates and representations, reinforcement learning involvement, adaptive learning rates and representations enhance the adaptability of reinforcement learning models. Evolutionary algorithm collaboration. Evolutionary algorithms can evolve adaptive learning rates or representations, allowing RL models to dynamically adjust to the characteristics of the environment. Hybrid evolutionary reinforcement learning (ERL) models. Reinforcement learning involvement. Reinforcement learning agents seek to learn optimal policies. Evolutionary algorithm collaboration. Hybrid evolutionary reinforcement learning models combine the strengths of both approaches, using evolution to optimize policies, particularly beneficial when facing complex and high-dimensional state action spaces. Escape local optima. Reinforcement learning involvement. RL models may get stuck in local optima during training. Evolutionary algorithm collaboration. Evolutionary algorithms are known for their ability to explore the solution space globally, helping reinforcement learning models escape local optima and discover better policies. Meta learning, reinforcement learning involvement. Meta learning enables reinforcement learning models to learn how to learn more efficiently. Evolutionary algorithm collaboration. Evolutionary algorithms can be employed in meta learning scenarios, evolving learning strategies that enhance the adaptability and learning speed of reinforcement learning models across various tasks. Co-evolutionary algorithms for multi-agent reinforcement learning. Reinforcement learning involvement. Multi-agent reinforcement learning involves multiple interacting agents. Evolutionary algorithm collaboration. Co-evolutionary algorithms can evolve policies for multiple agents, simultaneously facilitating the learning of collaborative or competitive strategies in multi-agent environments. Adversarial policy generation, reinforcement learning involvement. Reinforcement learning models may benefit from adversarial policies for robust training. Evolutionary algorithm collaboration. Evolutionary algorithms can generate adversarial policies to challenge and enhance the robustness of reinforcement learning models, particularly in adversarial environments. Human in the loop evolutionary algorithms. Reinforcement learning involvement. Incorporating human insights is valuable for refining reinforcement learning models. Evolutionary algorithm collaboration. Human in the loop evolutionary algorithms allow experts to guide the evolution process, incorporating domain knowledge and preferences into the reinforcement learning process. Evolutionary exploration for continuous action spaces, reinforcement learning involvement. Reinforcement learning in continuous action spaces requires effective exploration. Evolutionary algorithm collaboration. Evolutionary algorithms, particularly those designed for continuous spaces, can aid reinforcement learning models in exploring and optimizing policies in environments with continuous action spaces. In summary, the collaboration between reinforcement learning and evolutionary algorithms provides a versatile framework for addressing challenges such as exploration, optimization, and adaptability in complex environments. Evolutionary algorithms bring their strengths in global exploration, diversity maintenance, and meta learning, complementing the learning capabilities of RL agents. Reinforcement learning and pattern recognition. Reinforcement learning and pattern recognition collaborate in various ways to enable reinforcement learning agents to identify and respond to patterns in the environment. Pattern recognition techniques help reinforcement learning models understand complex relationships, make predictions, and improve decision making. Here is a comprehensive overview of how reinforcement learning collaborates with pattern recognition, state representation, and feature extraction. Reinforcement learning involvement. Reinforcement learning involves representing states for decision making. Pattern recognition collaboration. Pattern recognition techniques aid in feature extraction and state representation, enabling reinforcement learning models to capture relevant information from observations. Visual pattern recognition for perception. Reinforcement learning involvement. Reinforcement learning agents often perceive the environment through visual observations. Pattern recognition collaboration. Visual pattern recognition, such as image processing algorithms, assists RL models in extracting meaningful information from visual inputs, enhancing perception in tasks like computer vision or robotics. Speech and audio pattern recognition. Reinforcement learning involvement. RL models may interact with environments involving speech or audio cues. Pattern recognition collaboration. Pattern recognition in speech and audio signals helps reinforcement learning agents interpret and respond to auditory information, making them applicable in tasks like voice controlled agents or dialogue systems. Temporal pattern recognition. Reinforcement learning involvement. Temporal dependencies are crucial for sequential decision making in reinforcement learning. Pattern recognition collaboration. Pattern recognition techniques for time series data enable reinforcement learning models to identify and understand temporal patterns essential for tasks with dynamic and evolving environments. Sequential decision making with sequence patterns. Reinforcement learning involvement. Reinforcement learning agents make decisions sequentially over time. Pattern recognition, collaboration, recognition of sequence patterns asserts reinforcement learning models in understanding the sequential nature of tasks, facilitating more informed decision making. Pattern matching in observations, reinforcement learning involvement. RL models need to identify relevant patterns in observations. Pattern recognition collaboration. Pattern matching algorithms allow RL agents to recognize specific patterns in observations, aiding in tasks where certain configurations or structures are significant. Anomaly detection. Reinforcement learning involvement. Reinforcement learning agents may need to detect anomalies in the environment. Pattern recognition collaboration. Anomaly detection through pattern recognition helps RL models identify unexpected or abnormal states, enhancing their ability to handle unusual situations. Feature learning and representation in deep learning. Reinforcement learning involvement. Deep learning is often used for RL tasks to automatically learn features. Pattern recognition collaboration. Deep learning, a subset of pattern recognition, is employed to automatically learn hierarchical and abstract features from raw data, improving the representation of states in reinforcement learning models. Special pattern recognition. Reinforcement learning involvement. Reinforcement learning tasks may involve special relationships in the environment. Pattern recognition collaboration. Special pattern recognition techniques assist reinforcement learning models in understanding and leveraging special structures applicable in robotics, navigation, and other specially oriented tasks. Object recognition and tracking. Reinforcement learning involvement. RL agents may need to recognize and track objects in their environment. Pattern recognition collaboration, object recognition and tracking algorithms contribute to RL models' understanding of the spatial arrangement and movement of objects, enhancing decision making in tasks like robotic manipulation or autonomous vehicle. Pattern recognition for goal identification, reinforcement learning involvement. Reinforcement learning models aim to achieve specific goals. Pattern recognition, collaboration, identifying patterns related to goal states helps reinforcement learning agents recognize when they have achieved a desired outcome, guiding their decision making towards successful task completion. Contextual pattern recognition, reinforcement learning involvement. RL agents operate within specific contexts. Pattern recognition collaboration. Contextual pattern recognition allows RL models to adapt their behavior based on the context of the environment, improving the adaptability and robustness of decision making. Transfer learning with pattern recognition. Reinforcement learning involvement. Transfer learning enables reinforcement learning models to leverage knowledge from one task to improve performance in another. Pattern recognition collaboration. Transfer learning using pre-trained pattern recognition models allows reinforcement learning agents to benefit from features learned in related tasks, accelerating learning in new environments. Ensemble learning with pattern recognition models, reinforcement learning involvement. Ensemble methods enhance the stability and performance of RL models. Pattern recognition collaboration. Ensemble learning with multiple pattern recognition models provides a robust approach to handling diverse patterns and variations in the environment, improving the reliability of RL decision making. Human in the loop pattern recognition, reinforcement learning involvement. Incorporating human insights is valuable for refining RL models. Pattern recognition collaboration, human in the loop pattern recognition allows experts to guide the recognition process, ensuring that domain knowledge is appropriately incorporated into RL decision making. Explainability and interpretability. Reinforcement learning involvement. Understanding and explaining reinforcement learning decisions is essential for trust. Pattern recognition collaboration. Pattern recognition methods contribute to explainability by providing interpretable patterns and features, aiding in the transparent interpretation of reinforcement learning decisions. In summary, the collaboration between reinforcement learning and pattern recognition enhances the ability of reinforcement learning models to recognize, interpret, and respond to meaningful patterns in the environment. Pattern recognition techniques provide valuable tools for feature extraction, perception, and understanding complex structures, contributing to more effective and adaptive decision making in reinforcement learning tasks. Reinforcement learning and computer vision collaborate to address tasks that require visual perception, interpretation, and decision making. Computer vision techniques provide reinforcement learning models with the ability to understand and interact with visual information, allowing them to navigate and make decisions in environments with visual inputs. Here is a comprehensive overview of how reinforcement learning collaborates with computer vision. Visual perception for state representation. Reinforcement learning involvement. Reinforcement learning involves representing states for decision making. Computer vision collaboration. Computer vision techniques assist in visual perception, extracting relevant information from images or video frames to create informative state representations for reinforcement learning models. Object recognition and localization. Reinforcement learning involvement. RL agents may need to recognize and locate objects in the environment. Computer vision collaboration. Object recognition and localization algorithms in computer vision contribute to RL models understanding of the spatial arrangement of objects, aiding in tasks such as robotic manipulation or scene understanding. Semantic segmentation, reinforcement learning involvement, understanding the semantic content of visual scenes is crucial for RL tasks. Computer vision collaboration, semantic segmentation techniques help reinforcement learning models distinguish and understand different regions or objects within an image, providing a more detailed perception of the environment. Depth perception and 3D reconstruction. Reinforcement learning involvement. Depth information is essential for spatial awareness in RL. Computer vision collaboration. Computer vision methods for depth perception and 3D reconstruction assist RL agents in understanding the three-dimensional structure of the environment, crucial for tasks like navigation and obstacle avoidance. Future learning with convolutional neural networks, CNNS. Reinforcement learning involvement. Feature learning enhances RL models' ability to extract meaningful information. Computer vision collaboration, CNNS, commonly used in computer vision, are employed for feature learning from visual inputs, providing rich and hierarchical representations that improve the effectiveness of RL models. Visual attention mechanisms, reinforcement learning involvement, focusing on relevant visual information is crucial for RL decision making. Computer vision collaboration, visual attention mechanisms help RL models selectively process important regions of an image, improving efficiency and adaptability in tasks where attention to specific details is essential. Action recognition in videos, reinforcement learning involvement. RL agents may need to recognize and understand actions within video sequences. Computer vision collaboration. Action recognition algorithms in computer vision assist RL models in interpreting dynamic visual inputs, enabling them to respond appropriately to changing scenarios. Simultaneous localization and mapping, SLAM. Reinforcement learning involvement. Spatial awareness is crucial for RL navigation tasks. Computer vision collaboration. SLAM techniques in computer vision contribute to RL models' understanding of their location and surroundings, facilitating tasks like robotic exploration or navigation. Transfer learning with pre-trained visual models. Reinforcement learning involvement. Transfer learning enables RL models to leverage knowledge from pre-trained models. Computer vision collaboration. Pre-trained visual models, such as those for image classification or object detection, can be used in transfer learning scenarios, allowing RL agents to benefit from features learned in related tasks. Visual goal identification, reinforcement learning involvement. RL models often have specific goals to achieve. Computer vision collaboration. Computer vision aids reinforcement learning models in identifying visual cues related to goals, facilitating goal-directed decision-making and task completion. Human pose estimation. Reinforcement learning involvement. Understanding human poses is relevant for human-robot interaction or gesture-based control. Computer vision collaboration. Human pose estimation techniques contribute to RL models' understanding of human interactions, allowing them to respond appropriately to human gestures or movements. Visual affordance detection, reinforcement learning involvement. RL models may need to recognize visual affordances for effective interaction. Computer vision collaboration, affordance detection in computer vision helps RL agents identify actionable opportunities in the visual scene, guiding their decision making in tasks like object manipulation, object tracking. Reinforcement learning involvement. Tracking moving objects is crucial for dynamic environments. Computer vision collaboration, object tracking algorithms enable reinforcement learning models to maintain awareness of the movement and location of objects over time, enhancing decision making in tasks like surveillance or robotic tracking. scene understanding and contextual analysis, reinforcement learning involvement. RL agents benefit from understanding the broader context of the environment, computer vision collaboration, scene understanding techniques, and contextual analysis help RL models interpret the overall scene, improving their ability to make informed decisions based on the visual context. Visual simulators for training, reinforcement learning involvement. RL models often require extensive training in diverse environments. Computer vision collaboration, visual simulators utilizing computer vision techniques generate realistic visual inputs for RL models during training, facilitating the acquisition of robust and generalized policies. It seems there might be a typo in your question, and I am assuming you meant expert vision rather than export vision. If my assumption is incorrect, please clarify, and I'll be happy to address your question accordingly. Assuming you are referring to expert vision, here is a comprehensive overview of how reinforcement learning collaborates with expert vision. Expert label data for training. Reinforcement learning involvement. Reinforcement learning models benefit from learning from expert demonstrations. Expert vision collaboration. Expert vision provides labeled data such as demonstrations of optimal behavior which can be used to train and initialize reinforcement learning models, accelerating the learning process. Imitation learning and behavioral cloning. Reinforcement learning involvement. Imitation learning allows RL models to learn from expert demonstrations. Expert vision collaboration. Expert vision guides the process of behavioral cloning where RL models imitate the observed behavior of experts, serving as an effective starting point for subsequent reinforcement learning. Reward shaping from expert feedback. Reinforcement learning involvement. RL models often rely on reward signals for learning. Expert vision collaboration. Expert vision contributes to reward shaping by providing insights into desirable behaviors. Expert feedback can be used to design reward functions that guide RL models toward expert-like performance. Mimicking expert policies. Reinforcement learning involvement. Reinforcement learning models aim to learn policies that lead to optimal outcomes. Expert vision collaboration. Expert vision assists RL models in mimicking the decision-making strategies of experts, helping the models approach or surpass the level of performance demonstrated by human vision. Transfer learning from expert knowledge. Reinforcement learning involvement. Transfer learning allows RL models to leverage knowledge from one domain to another. Expert vision collaboration. Transfer learning from expert knowledge involves adapting RL models to new tasks or environments by leveraging insights gained from expert vision, enabling faster adaptation and improved generalization. Combining RL and expert strategies. Reinforcement learning involvement. RL models seek to learn optimal strategies through trial and error. Expert vision collaboration. Combining RL with expert strategies allows for a hybrid approach where RL models benefit from both experiential learning and the refined strategies provided by expert vision, guiding exploration with expert insights. Reinforcement learning involvement. Exploration is a critical aspect of RL to discover optimal strategies. Expert vision collaboration. Expert insights guide RL models in their exploration by providing valuable information on promising regions of the state or action space, improving the efficiency of learning. Human in the loop expert guidance. Reinforcement learning involvement. Incorporating human insights enhances RL performance. Expert vision collaboration. Human in the loop expert guidance involves experts providing real-time feedback and corrections to the RL model during the learning process, refining the model behavior based on expert vision. expert-defined evaluation matrix, reinforcement learning involvement. Evaluating RL models requires defining relevant matrix. Expert VN collaboration. Expert VN helps define evaluation matrix that align with human goals and preferences, ensuring that RL models are assessed based on criteria deemed important by domain experts. Continuous feedback loop with experts. Reinforcement learning involvement. Continuous improvement is crucial for RL models. Expert VN collaboration. Establishing a feedback loop with experts ensures ongoing collaboration, allowing RL models to adapt to evolving requirements and benefit from expert insights throughout their operational lifespan. Validation of learned policies. Reinforcement learning involvement. Validating learned policies is essential for robust performance. Expert VN collaboration. Expert VN aids in the validation process by assessing whether RL models' learned policies align with expert expectations and are suitable for deployment in real-world scenarios. Combining human and RL decision making. Reinforcement learning involvement. RL models may operate in conjunction with human decision makers. Expert VN collaboration. Combining human and RL decision making involves integrating expert VN into the decision making process, creating collaborative systems where the strengths of both humans and machines are leveraged. Adapting to changes in expert strategies. Reinforcement learning involvement. RL models should adapt to dynamic environments. Expert VN collaboration. Expert VN aids reinforcement learning models in adapting to changes by providing insights into updated strategies or priorities, ensuring the models remain effective in evolving scenarios. Incremental learning with expert guidance. Reinforcement learning involvement. Incremental learning allows RL models to adapt to new information. Expert VN collaboration. Expert guidance facilitates incremental learning, guiding RL models in updating their knowledge and behavior based on the latest insights provided by expert VN. Robustness testing with expert scenarios. Reinforcement learning involvement. Testing RL models for robustness is crucial. Expert VN collaboration. Expert scenarios are valuable in robustness testing, helping ensure that RL models perform reliably across a range of situations, including those identified by expert VN. Ensuring ethical and human-centric artificial intelligence. Reinforcement learning involvement. Ethical considerations are essential in artificial intelligence development. Expert VN collaboration. Expert VN contributes to the ethical development. Reinforcement learning and robotics collaborate to enable intelligent decision-making and control in robotic systems. RL provides a framework for robots to learn optimal behaviors through interaction with their environment. Here is a comprehensive overview of how reinforcement learning collaborates with robotics. Simulated environments for training. Reinforcement learning involvement. RL models require training in diverse environments. Robotics collaboration. Simulated environments in robotics allow RL models to train in virtual settings, providing a safe and efficient way to learn before deploying on physical robots. End-to-end learning. Reinforcement learning involvement. RL enables end-to-end learning of policies. Robotics collaboration. End-to-end learning in robotics involves RL models directly mapping sensor inputs to motor outputs, simplifying the design of control systems for robots. Robotics tasks as RL problems. Reinforcement learning involvement. RL formulates problems as Markov decision processes. Robotics collaboration. Robotics tasks such as grasping or navigating are framed as RL problems, allowing robots to learn optimal policies for these tasks. Motion planning and control. Reinforcement learning involvement. RL models learn motion policies for control. Robotics collaboration. RL contributes to motion planning and control in robotics, enabling robots to learn adaptive and efficient motion strategies. Adaptive and agile movement, reinforcement learning involvement. RL facilitates learning adaptive movement strategies. Robotics collaboration. RL models enhance the agility of robotic movement by learning from interactions, enabling robots to adapt to different terrains and environments. Robotic manipulation and grasping, reinforcement learning involvement. RL models learn manipulation policies. Robotics collaboration. RL is applied to robotic manipulation, allowing robots to learn grasping strategies and adapt to various objects and shapes. Learning from demonstrations. Reinforcement learning involvement. Imitation learning involves learning from expert demonstrations. Robotics collaboration. Robots learn from human demonstrations through RL, allowing them to acquire complex skills demonstrated by experts. Real world transfer learning, reinforcement learning involvement. Transfer learning enables models to apply knowledge from one domain to another. Robotics collaboration. Transfer learning in robotics involves applying RL models trained in simulation to real world robotic systems, leveraging knowledge gained in virtual environments. Continuous learning for robot adaptability, reinforcement learning involvement. Continuous learning enables models to adapt over time. Robotics collaboration, RL contributes to continuous learning in robotics, allowing robots to adapt and improve their performance through ongoing interactions with the environment. Sensor fusion for perception, reinforcement learning involvement. RL models use sensory information for decision making. Robotics collaboration, sensor fusion techniques in robotics integrate data from multiple sensors, providing more comprehensive information for RL models to make informed decisions. Learning robotics control policies, reinforcement learning involvement. RL models learn control policies. Robotics collaboration, RL is applied to learn robotics control policies, enabling robots to autonomously control their movements and actions. Exploration and mapping, reinforcement learning involvement. RL involves exploration of the environment. Robotics collaboration, robotic utilize RL to explore and map unknown environments, contributing to autonomous navigation and mapping capabilities. Human robot collaboration, reinforcement learning involvement. RL facilitates collaborative decision making. Robotics collaboration, human robot collaboration involves RL models that learn to work alongside humans, adapting to human preferences and optimizing joint tasks. Reinforcement learning in swarm robotics, reinforcement learning involvement. RL principles extend to multi-robot systems. Robotics collaboration, swarm robotics leverages RL for collective decision making, enabling groups of robots to coordinate and achieve complex objectives. Learning robotics, policies under constraints. Reinforcement learning involvement. RL models learn policies under specified constraints. Robotics collaboration. RL is applied to learn robotics policies that adhere to safety constraints, enabling robots to operate within predefined limits. Adaptive control in dynamic environments. Reinforcement learning involvement. RL models adapt to dynamic environments. Robotics collaboration. Adaptive control in robotics involves RL model learning to navigate and perform tasks in dynamic and changing environments, improving the versatility of robotic systems. In summary, the collaboration between reinforcement learning and robotics empowers robots to learn and adapt to complex tasks, enhancing their autonomy, adaptability, and decision-making capabilities in various environments. RL provides a versatile framework for robots to acquire skills, optimize behaviors, and tackle challenges in both simulated and real-world scenarios. Speech recognition. Reinforcement learning and speech recognition collaborate to improve the performance and adaptability of systems that convert spoken language into text. This collaboration allows reinforcement learning models to learn and optimize speech recognition processes for various applications. Here is a comprehensive overview of how reinforcement learning collaborates with speech recognition. State representation from audio input. Reinforcement learning involvement. Reinforcement learning models operate based on state representations. Speech recognition collaboration. Audio signals are transformed into state representations for RL models, allowing them to learn and make decisions based on speech input. Feature extraction and pre-processing. Reinforcement learning involvement. Effective feature extraction is essential for reinforcement learning performance. Speech recognition collaboration. Speech recognition systems pre-process audio signals, extracting features such as spectrograms or MFCCS, which serve as informative inputs for reinforcement learning models. Reward design for speech recognition. Reinforcement learning involvement. RL models learn from rewards to optimize their behavior. Speech recognition collaboration. Reward signals are designed based on the accuracy of speech recognition. RL models are trained to maximize rewards by improving transcription, accuracy, and reducing errors. Exploration, exploitation for adaptation. Reinforcement learning involvement. Balancing exploration and exploitation is crucial in reinforcement learning. Speech recognition collaboration. RL models explore various approaches to adapt speech recognition systems, learning optimal policies for exploitation in different environments and for diverse speakers. Online learning for adaptability. Reinforcement learning involvement. Online learning allows models to adapt continuously. Speech recognition collaboration. RL models in speech recognition systems leverage online learning to adapt to changes in speech patterns, environmental conditions, or user accents over time. Incremental vocabulary learning. Reinforcement learning involvement. Incremental learning allows model to adapt to new information. Speech recognition collaboration. Reinforcement learning models can incrementally learn new words or phrases, enhancing vocabulary adaptation in speech recognition systems. Contextual understanding of speech. Reinforcement learning involvement. RL models benefit from understanding contextual information. Speech recognition collaboration. Speech recognition systems use RL to understand contextual cues, improving the interpretation of spoken language in various situations. User feedback integration. Reinforcement learning involvement. User feedback helps refine RL models. Speech recognition collaboration. User feedback on speech recognition accuracy is integrated into the RL training process, allowing model to adapt and improve based on real-world user interactions. Multimodal integration with speech. Reinforcement learning involvement. RL models can benefit from multimodal inputs. Speech recognition collaboration. Speech recognition systems integrate RL with other modalities such as visual cues or context to enhance overall understanding and accuracy. Handling noisy environments. Reinforcement learning involvement. Reinforcement learning models learn to operate in noisy conditions. Speech recognition collaboration. RL is applied to improve speech recognition robustness in noisy environments, enabling systems to adapt and perform well even in challenging acoustic conditions. Personalized speech recognition. Reinforcement learning involvement. Personalization improves RL model performance. Speech recognition collaboration. RL models enable Personalized speech recognition by adapting to individual users' speech patterns, accents, and preferences. Transfer learning across speech tasks. Reinforcement learning involvement. Transfer learning aids RL models in leveraging knowledge across tasks. Speech recognition collaboration. Transfer learning is applied in speech recognition to allow RL models to benefit from pre-trained models or knowledge acquired from related speech tasks. Continuous speech recognition improvement. Reinforcement learning involvement. Continuous improvement is a goal in RL. Speech recognition collaboration. RL models contribute to continuous improvement in speech recognition systems by adapting to changing conditions and user needs. Adaptive speech model architecture. Reinforcement learning involvement. RL models can adapt their architectures. Speech recognition collaboration. RL is applied to adapt the architecture of speech recognition models, optimizing their structure for improved performance and efficiency. Efficient resource allocation. Reinforcement learning involvement. RL models learn efficient resource allocation. Speech recognition collaboration. RL is used to optimize the allocation of computational resources in speech recognition systems, improving efficiency and real-time performance. Human in the loop refinement. Reinforcement learning involvement. Human insights enhance RL models. Speech recognition collaboration. Human in the loop refinement involves experts providing feedback to fine-tune RL models, ensuring the speech recognition system aligns with human expectations and preferences. In summary, the collaboration between reinforcement learning and speech recognition enables systems to learn, adapt, and continuously improve their ability to accurately transcribe spoken language. Reinforcement learning models contribute to the adaptability, efficiency, and contextual understanding of speech recognition systems, making them more versatile and effective in diverse real-world scenarios. Genetic algorithms. Reinforcement learning and genetic algorithms can collaborate to address complex optimization problems and enhance the performance of learning systems. The combination of RL and GA provides a powerful approach for solving problems where a search space needs to be explored efficiently. Here is a comprehensive overview of how RL collaborates with genetic algorithms. Optimization problem formulation. Reinforcement learning involvement. RL addresses problems as Markov decision processes. Genetic algorithm collaboration. Genetic algorithms work on optimization problems where a population of candidate solution evolves over generations. RL formulates problems as MDPS, and generic algorithms can optimize policies or parameters within this framework. Policy search with genetic encoding. Reinforcement learning involvement. Reinforcement learning models learn policies for decision making. Genetic algorithm collaboration. Genetic algorithms can encode policies or parameters into a genetic representation, allowing reinforcement learning models to evolve and optimize decision-making strategies over successive generations. Population-based exploration. Reinforcement learning involvement. RL involves exploration of state and action spaces. Genetic algorithm collaboration. Genetic algorithms maintain a population of potential solutions, promoting exploration across the solution space. Reinforcement learning models benefit from population-based exploration to discover diverse strategies. Crossover for policy combination. Reinforcement learning involvement. RL models explore new policies through mutation. Genetic algorithm collaboration. Crossover operations in generic algorithms combine features or policies from different individuals in the population, enabling reinforcement learning models to explore combinations of successful strategies. Mutation for policy variation. Reinforcement learning involvement. RL involves introducing variability through mutation. Genetic algorithm collaboration. Mutation operations in generic algorithms introduce small changes to individuals in the population, allowing RL models to explore variations of policies and parameters, adaptive parameter tuning, reinforcement learning involvement. RL models may have hyperparameters that need tuning. Genetic algorithm collaboration. Genetic algorithms can optimize hyperparameters by evolving a population of candidate solutions, aiding reinforcement learning models in adapting their parameters for improved performance. Parallel evolutions for efficiency. Reinforcement learning involvement. RL models are often computationally demanding to train. Genetic algorithm collaboration. Genetic algorithms allow for parallel evolutions of multiple individuals in the population, enhancing the efficiency of RL training by evaluating diverse strategies concurrently. Fitness function definition. Reinforcement learning involvement. RL models improve based on a reward signal. Genetic algorithm collaboration. Fitness functions in genetic algorithms define the quality of individuals in the population. RL models benefit from the definition of fitness functions that align with the learning objectives. Combining reinforcement learning and evolutionary strategies. Reinforcement learning involvement. RL models can use evolution strategies for optimization. Genetic algorithm collaboration. Combining RL with evolutionary strategies involve using genetic algorithms to optimize policies or parameters in reinforcement learning models, providing an additional optimization layer. Transfer of knowledge across generations. Reinforcement learning involvement. Transfer learning enables knowledge reuse. Genetic algorithm collaboration. Genetic algorithms facilitate knowledge transfer across generations, allowing RL models to leverage successful strategies from previous populations to accelerate learning. Hierarchical optimization. Reinforcement learning involvement. RL may involve hierarchical decision making. Genetic algorithm collaboration. Genetic algorithms can optimize parameters at different levels of a hierarchy, contributing to the hierarchical optimization of RL models with complex decision structures. Multi-objective optimization. Reinforcement learning involvement. Reinforcement learning may involve balancing multiple objectives. Genetic algorithm collaboration. Genetic algorithms support multi-objective optimization, enabling reinforcement learning models to find a trade-off between conflicting objectives, such as maximizing rewards and minimizing exploration. Dynamic environment adaptation. Reinforcement learning involvement. RL models adapt to dynamic environments. Genetic algorithm collaboration. GAS contribute to dynamic adaptation by evolving solutions that can cope with changes in the environment, enhancing the adaptability of RL models. Population diversity maintenance. Reinforcement learning involvement. Diversity is essential for robust reinforcement learning models. Genetic algorithm collaboration. Genetic algorithms maintain population diversity through mechanisms like elitism, preventing premature convergence, and assisting RL models in exploring a broader solution space. Evolutionary reinforcement learning frameworks. Reinforcement learning involvement. RL frameworks provide the infrastructure for learning algorithms. Genetic algorithm collaboration. Evolutionary reinforcement learning frameworks integrate RL algorithms with GAS, allowing for seamless collaboration and enhanced optimization capabilities. Human in the loop strategy evolution. Reinforcement learning involvement. Human insights contribute to reinforcement learning model evolution. Genetic algorithm collaboration. In a human in the loop approach, experts provide feedback on the success of strategies evolved by GAS, improving reinforcement learning models through a combination of evolutionary optimization and human expertise. In summary, the collaboration between reinforcement learning and genetic algorithms offers a powerful approach for addressing complex optimization problems and enhancing the adaptability and efficiency of learning systems. The combination of reinforcement learning's decision-making capabilities with GA's evolutionary optimization methods provide a versatile framework for solving challenging problems in various domains. Swarm intelligence. Reinforcement learning and swarm intelligence collaborate to address complex problems by drawing inspiration from the collective behaviors of swarm in nature. This collaboration enables system to learn and adapt through interactions, parallelism, and decentralized decision making. Here is a comprehensive overview of how reinforcement learning collaborates with swarm intelligence. Decentralized decision making. Reinforcement learning involvement. RL models learn optimal policies for decision making. Swarm intelligence collaboration. Swarm intelligence emphasized decentralized decision making, where reinforcement learning models in a swarm make decisions independently, often based on local information, contributing to overall emergent behavior. Population-based exploration, reinforcement learning involvement. RL involves exploration to discover optimal strategies. Swarm intelligence collaboration. Swarm systems inspired by swarm intelligence explore a solution space with multiple individuals concurrently, enhancing the exploration efficiency of reinforcement learning models and promoting diversity in strategies. Distributed learning in multi-agent systems. Reinforcement learning involvement. Reinforcement learning models can operate in multi-agent environments. Swarm intelligence collaboration. Multi-agent systems inspired by SI distribute learning across agents, allowing RL models to collaborate and adapt collectively, often in scenarios where centralized control is impractical. Adaptive communication strategies. Reinforcement learning involvement. RL models may require communication for coordination. Swarm intelligence collaboration. SI principles guide the development of adaptive communication strategies among RL agents, enabling effective collaboration through decentralized communication channels. Self-organization and emergent behavior. Reinforcement learning involvement. RL models adapt their behavior based on rewards. Swarm intelligence collaboration. Swarm intelligence promotes self-organization, where RL models in a swarm adjust their actions based on local interactions, leading to emergent behaviors that collectively achieve goals. Learning from neighbors. Reinforcement learning involvement. RL models can learn from the experiences of other agents. Swarm intelligence collaboration. In swarm inspired systems, RL models exchange information with nearby agents, allowing them to learn from the experiences and observations of their neighbors, contributing to collective learning. Collective decision fusion. Reinforcement learning involvement. RL models may aggregate information for decision making. Swarm intelligence collaboration. Swarm systems fuse decisions collectively, where RL models share and combine their individual decisions, leading to a consensus that reflects the collective intelligence of the swarm. Hierarchical swarm structures. Reinforcement learning involvement. RL may involve hierarchical decision making. Swarm intelligence collaboration. Hierarchical structures in swarm-inspired systems allow RL models to operate at different levels, with each level contributing to overall decision making, enabling more complex and adaptive behavior. Dynamic task allocation. Reinforcement learning involvement. RL models adapt to changing task requirements. Swarm intelligence collaboration. Swarm systems dynamically allocate tasks among RL agents, ensuring efficient use of resources and adaptive responses to evolving environmental conditions. Ant colony optimization and exploration. Reinforcement learning involvement. RL models explore environments for optimal solutions. Swarm intelligence collaboration. Ant colony optimization, a subset of swarm intelligence inspires RL models to explore environments efficiently, leveraging principles such as pheromone communication and stigmergy. Particle swarm optimization for parameter tuning, reinforcement learning involvement. RL models may have parameters that require tuning. Swarm intelligence collaboration, particle swarm optimization. A swarm intelligence technique is applied to optimize RL model parameters, assisting in the adaptation of models to specific tasks or environments. Robustness through redundancy. Reinforcement learning involvement. Robust RL models can handle uncertainties. Swarm intelligence collaboration. SI emphasizes redundancy in swarm systems, enhancing the robustness of RL models by allowing for multiple agents to perform similar tasks, ensuring continued functionality even if individual agents fail. Dynamic role assignment, reinforcement learning involvement. RL models can adapt their roles based on learning. Swarm intelligence collaboration, dynamic role assignment in swarm inspired RL systems allows agents to adapt their roles based on changing conditions, optimizing their contributions to the collective goal. Learning from swarm navigation, reinforcement learning involvement. RL models learn navigation policies. Swarm intelligence collaboration. RL model draw inspiration from swarm navigation behaviors where agents collectively navigate and adapt their paths, contributing to improved navigation strategies. Cooperative task execution, reinforcement learning involvement. RL models can operate collaboratively. Swarm intelligence collaboration, swarm inspired cooperative task execution involves RL models working together to achieve common objectives, demonstrating the power of decentralized coordination and cooperation. Human swarm interaction and collaboration. Reinforcement learning involvement. Human insights can guide RL model development. Swarm intelligence collaboration. Human swarm interaction involves collaboration between humans and RL driven swarms where human feedback and guidance enhance the adaptability and effectiveness of the collective intelligence. In summary, the collaboration between reinforcement learning and swarm intelligence combines the adaptability of RL models with the decentralized collective decision-making principles of swarm systems. This synergy allows for the development of intelligent systems capable of robust, adaptive, and efficient behavior in various complex environments. Reinforcement learning and transfer learning. Reinforcement learning collaborates with transfer learning to leverage knowledge gained in one task to improve the learning and performance of a related task. This collaboration is particularly useful when the data or experience obtained in a source task can be beneficial for accelerating learning or enhancing generalization in a target task. Here is a comprehensive overview of how reinforcement learning collaborates with transfer learning. Definition of transfer learning in reinforcement learning. Reinforcement learning involvement. Reinforcement learning focuses on learning optimal decision-making strategies. Transfer learning collaboration. Transfer learning in reinforcement learning involves utilizing knowledge gained from one task, source task, to improve the learning or performance of another related task, target task. Source and target task definition. Reinforcement learning involvement. Reinforcement learning tasks involve defining the state, action, and reward spaces. Transfer learning collaboration, identifying source and target tasks, is crucial in transfer learning. Reinforcement learning models aim to transfer knowledge from the source task to expedite learning or enhance performance in the target task. Shared state spaces, reinforcement learning involvement. Reinforcement learning models operate within defined state spaces. Transfer learning collaboration. Transfer learning benefits from shared state spaces between the source and target tasks. Common feature or representations learned in the source task can aid the reinforcement learning model in the target task. Knowledge transfer mechanisms. Reinforcement learning involvement. Reinforcement learning models learn from experiences and rewards. Transfer learning collaboration. Knowledge transfer mechanisms in transfer learning involve adapting learned features, policies, or values from the source task to the target task, guiding the reinforcement learning model in its learning process. Fine-tuning of parameters. Reinforcement learning involvement. Reinforcement learning models have parameters that influence learning. Transfer learning collaboration. Fine-tuning involves adjusting specific parameters of the RL model, such as neural network weights, to align with the target task while preserving knowledge gained from the source task. Domain adaptation techniques. Reinforcement learning involvement. RL models operate in specific domains. Transfer learning collaboration. Domain adaptation techniques help RL models adapt to the target domain by adjusting to differences between the source and target domains, facilitating effective knowledge transfer. Pre-training source task. Reinforcement learning involvement. RL models may require extensive training. Transfer learning collaboration. Pre-training involves training the RL model in the source task, allowing it to acquire general features or policies that can be useful in the subsequent target task. Shared policies across tasks. Reinforcement learning involvement. RL models learn decision-making policies. Transfer learning collaboration. Transfer learning promotes the sharing of decision-making policies across tasks, enabling the RL model to generalize well to the target task using knowledge from the source task. Sequential transfer learning. Reinforcement learning involvement. RL often involves learning sequences of actions. Transfer learning collaboration. In sequential transfer learning, reinforcement learning models transfer knowledge across a sequence of related tasks, allowing them to accumulate expertise over multiple stages. Task hierarchy and compositionality. Reinforcement learning involvement. Reinforcement learning models may operate hierarchically. Transfer learning collaboration. Task hierarchy in transfer learning involves decomposing complex tasks into simpler subtasks, aiding reinforcement learning models in transferring knowledge hierarchically between source and target tasks. Memory augmentation for knowledge retention. Reinforcement learning involvement. Reinforcement learning models may use memory for experience replay. Transfer learning collaboration. Memory augmentation involves preserving important experiences from the source task to facilitate knowledge retention and transfer to the target task in reinforcement learning. Meta learning for rapid adaptation. Reinforcement learning involvement. Reinforcement learning models learn from experiences to adapt. Transfer learning collaboration. Meta learning in transfer learning enables RL models to learn how to learn efficiently, leading to rapid adaptation to new tasks by leveraging knowledge from the source task. Zero shot and few shot learning. Reinforcement learning involvement. RL models aim to generalize from limited data. Transfer learning collaboration. Zero shot and few shot learning in transfer learning involve training RL models to perform tasks with minimal data by transferring knowledge from the source task, demonstrating the adaptability of reinforcement learning models. Ensemble methods for knowledge integration. Reinforcement learning involvement. RL models can benefit from ensemble learning. Transfer learning collaboration. Ensemble methods in transfer learning involves integrating knowledge from multiple reinforcement learning models trained on diverse source tasks, enhancing the reinforcement learning model's adaptability and generalization in the target task. Unsupervised and self-supervised learning. Reinforcement learning involvement. Reinforcement learning models learn from both supervised and unsupervised signals. Transfer learning collaboration. Unsupervised and self-supervised learning methods in transfer learning allow reinforcement learning models to extract valuable information from unlabeled data in the source task, improving performance in the target task. Continuous transfer learning for evolving environments. Reinforcement learning involvement. Reinforcement learning models must adapt to dynamic environments. Transfer learning collaboration. Continuous transfer learning involves RL models adapting to changes in the environment over time, ensuring the sustained relevance and effectiveness of knowledge transferred from the source task. In summary, the collaboration between reinforcement learning and transfer learning enhances the efficiency and adaptability of reinforcement learning models by leveraging knowledge acquired in one task to improve performance in a related task. Transfer learning provides a valuable framework for accelerating learning, overcoming data limitations, and promoting generalization in reinforcement learning applications across diverse domains. Adversarial learning. Reinforcement learning collaborates with adversarial learning to address challenges such as robustness, security, and the exploration of diverse strategies. Adversarial learning introduces adversarial elements that actively attempt to deceive or challenge the RL model during training, leading to more robust and adaptable decision making. Here is a comprehensive overview of how RL collaborates with adversarial learning. Definition of adversarial learning in reinforcement learning. Reinforcement learning involvement. Reinforcement learning focuses on learning optimal policies through interactions. Adversarial learning collaboration. Adversarial learning in RL involves introducing adversarial elements or perturbations during training to enhance the model's robustness and improve its generalization to unforeseen conditions. Adversarial environments and challenges. Reinforcement learning involvement. RL models operate in dynamic and uncertain environments. Adversarial learning collaboration. Adversarial environments introduce challenges that test the robustness of RL models, helping them learn strategies that are more resilient to adversarial perturbation. Generative adversarial networks GANS in reinforcement learning. Reinforcement learning involvement. RL models optimize decision-making policies. Adversarial learning collaboration. Generative adversarial networks GANS are applied to reinforcement learning scenarios, introducing adversarial agents that generate perturbations to the reinforcement learning model's inputs, encouraging the model to become more robust. Adversarial policies for exploration. Reinforcement learning involvement. RL models explore the state action space to learn optimal policies. Adversarial learning collaboration. Adversarial policies are introduced to the RL training process, challenging the model to explore and learn strategies that are robust to deceptive or adversarial actions from opponents. Transferable adversarial examples. Reinforcement learning involvement. RL models generalize from training to unseen scenarios. Adversarial learning collaboration. Transferable adversarial examples crafted to deceive the RL model are used to test the generalization capabilities of the model, encouraging it to learn policies that are less vulnerable to adversarial inputs. Defensive distillation techniques. Reinforcement learning involvement. RL models may need defenses against adversarial attacks. Adversarial learning collaboration. Defensive distillation involves training the RL model to be resistant to adversarial perturbations by incorporating techniques from adversarial learning such as generating adversarial examples during training. Reward shaping against adversaries. Reinforcement learning involvement. RL model optimizes for rewards to learn policies. Adversarial learning collaboration. Reward shaping strategies are employed to guide the RL model in learning policies that are resilient to adversarial actions, ensuring that optimal behavior considers potential adversarial challenges. Adversarial training for policy robustness. Reinforcement learning involvement. RL models learn from interactions to improve policies. Adversarial learning collaboration. Adversarial training involves exposing the RL model to adversarial scenarios during training, promoting the development of policies that can withstand adversarial perturbations. Incorporating uncertainty for robustness. Reinforcement learning involvement. RL model may need to handle uncertainty in the environment. Adversarial learning collaboration. Incorporating uncertainty. Modeling in RL considers the presence of adversarial elements, helping the model make robust decisions even when facing unpredictable adversarial actions. Adversarial reinforcement learning frameworks. Reinforcement learning involvement. RL frameworks define the structure for learning algorithms. Adversarial learning collaboration. Adversarial reinforcement learning frameworks integrate RL algorithms with adversarial learning techniques, creating a unified structure to enhance the robustness of RL models. Multi-agent adversarial environments. Reinforcement learning involvement. RL models operate in environments with multiple agents. Adversarial learning collaboration. Multi-agent adversarial environments involve introducing adversarial agents that actively challenge the RL model decision making, fostering the development of strategies that can withstand diverse adversarial actions. Adversarial imitation learning. Reinforcement learning involvement. RL models may learn from expert demonstrations. Adversarial learning collaboration. Adversarial imitation learning incorporates adversarial elements into the learning process, challenging the reinforcement learning model to distinguish between expert and adversarial demonstrations, enhancing its ability to handle deceptive inputs. Policy evaluation under adversarial conditions. Reinforcement learning involvement. RL models evaluate policies based on rewards. Adversarial learning collaboration. Evaluating policies under adversarial conditions involves testing the RL model's performance against adversarial agents, ensuring that learned policies are effective even in the presence of deceptive actions. Safe exploration in adversarial contexts. Reinforcement learning involvement. RL models explore to discover optimal policies. Adversarial learning collaboration. Safe exploration techniques in RL consider adversarial contexts, preventing the RL model from taking unsafe or exploitable actions during the learning process. Adversarial attacks and countermeasures. Reinforcement learning involvement. RL models may face adversarial attacks. Adversarial learning collaboration. Adversarial attacks and countermeasures involve actively defending RL models against intentional adversarial manipulation, promoting the development of more resilient policies. Human in the loop for adversarial evolution. Reinforcement learning involvement. Human insights contribute to RL model evolution. Adversarial learning collaboration. In a human in the loop approach, experts provide insights on adversarial scenarios, aiding in the evolution and improvement of RL models against potential real-world adversarial challenges. In summary, the collaboration between reinforcement learning and adversarial learning enhances the robustness and adaptability of reinforcement learning models by introducing challenges and uncertainties during training. Adversarial learning techniques actively contribute to the development of reinforcement learning models that can make effective decisions even in the presence of intentional adversarial perturbation or deceptive actions. Quantum computing. Reinforcement learning can potentially collaborate with quantum computing (QC) to address complex computational problems more efficiently. Quantum computing leverages the principles of quantum mechanics to perform computations that classical computers find challenging. While the field is still in its early stages, there are emerging possibilities for synergy between RL and QC. Here is a comprehensive overview. Introduction to Quantum Computing in Reinforcement Learning. Reinforcement Learning Involvement. RL focuses on learning optimal decision-making strategies. Quantum Computing Collaboration. Quantum computing introduces a new paradigm for computation using qubits and quantum gates, potentially allowing RL algorithms to leverage quantum properties for faster and more efficient computations. Quantum agents and states. Reinforcement learning involvement. RL agents make decisions based on states. Quantum computing collaboration. Quantum states, represented by qubits, can potentially encode complex information, offering a quantum representation of reinforcement learning states that may lead to more compact and expressive state spaces. Quantum superposition for state representation. Reinforcement learning involvement. RL models represent states in the environment. Quantum computing collaboration. Quantum superposition allows qubits to exist in multiple states simultaneously, enabling more efficient representation of RL states and potentially enhancing exploration in state spaces. Quantum entanglement for correlated states. Reinforcement learning involvement. RL models learn correlations between states and actions. Quantum computing collaboration. Quantum entanglement links qubits in correlated states, providing a potential mechanisms for RL models to efficiently capture and utilize correlations between different aspects of the environment. Quantum gates for policy and value functions. Reinforcement learning involvement. RL models learn policies and value functions. Quantum computing collaboration. Quantum gates can be employed to manipulate quantum states, offering a novel approach for implementing policy and value functions in RL algorithms, potentially leading to more efficient computations. Quantum parallelism for exploration. Reinforcement learning involvement. RL involves exploration of state action spaces. Quantum computing collaboration. Quantum parallelism allows multiple quantum states to be processed simultaneously, potentially accelerating exploration strategies in RL algorithms, especially in scenarios with large state spaces. Quantum annealing for optimization problems. Reinforcement learning involvement. RL models may face optimization challenges. Quantum computing collaboration. Quantum annealing, a quantum optimization technique, can be applied to address complex optimization problems encountered in RL, potentially leading to faster convergence and improved performance. Hybrid quantum classical RL algorithms. Reinforcement learning involvement. RL algorithms often operate on classical computers. Quantum computing collaboration. Hybrid algorithms combine classical and quantum processing, allowing RL models to leverage the strengths of both classical and quantum computing for more efficient learning and decision making. Quantum algorithms for RL training. Reinforcement learning involvement. RL models undergo training to optimize policies. Quantum computing collaboration. Quantum algorithms can be explored for RL training processes, potentially accelerating the convergence of RL algorithms by leveraging quantum parallelism and optimization techniques. Quantum machine learning libraries. Reinforcement learning involvement. RL libraries provide framework for algorithm implementation. Quantum computing collaboration. Quantum machine learning libraries offer tools and frameworks for integrating quantum algorithms with RL models, facilitating experimentation and development in the collaboration between RL and QC. Quantum reinforcement learning frameworks. Reinforcement learning involvement. RL frameworks define the structure for learning algorithms. Quantum computing collaboration. Quantum reinforcement learning frameworks integrate RL algorithms with quantum components, providing a structured approach for developing RL models that leverage the capabilities of quantum computing, quantum feature spaces for representation, reinforcement learning involvement. RL models benefit from effective feature representation, quantum computing collaboration. Quantum feature spaces enable the encoding of complex features efficiently, potentially enhancing the representation and learning capabilities of RL models. Quantum advantage for specific RL tasks. Reinforcement learning involvement. RL models address diverse tasks. Quantum computing collaboration. Quantum computing may offer advantages for special RL tasks, such as solving certain optimization problems or simulating quantum environments, leading to performance improvements in those specific domains. Quantum memory for sequential decision making. Reinforcement learning involvement. RL models make sequential decisions. Quantum computing collaboration. Quantum memory techniques can potentially enhance RL models' ability to handle sequential decision making, offering advantages in scenarios with intricate temporal dependencies. Quantum communication for multi-agent reinforcement learning. Reinforcement learning involvement. RL models may operate in multi-agent environments. Quantum computing collaboration. Quantum communication principles can be explored to facilitate communication and coordination among RL agents in multi-agent environments, potentially leading to more efficient collaboration. Quantum safe RL for security. Reinforcement learning involvement. RL models may be vulnerable to adversarial attacks. Quantum computing collaboration. Quantum safe reinforcement learning involves leveraging quantum resistant algorithms to enhance the security of RL models, protecting them against potential adversarial actions. In summary, the collaboration between reinforcement learning and quantum computing presents exciting possibilities for advancing the capabilities of RL algorithms, particularly in addressing complex optimization problems, enhancing representation capabilities, and exploring new avenues for more efficient decision making. While the field is still evolving, the integration of quantum computing principles holds potential for significant advancements in the realm of reinforcement learning. Cognitive computing. Reinforcement learning and cognitive computing can collaborate to create intelligent systems that mimic human cognitive functions, while reinforcement learning focuses on learning optimal decision-making strategies through interactions. Cognitive computing involves technologies that simulate aspects of human cognition, such as perception, reasoning, and problem solving. Here is a comprehensive overview of how reinforcement learning collaborates with cognitive computing. Introduction to cognitive computing in reinforcement learning. Reinforcement learning involvement. RL models optimize decision-making policies. Cognitive computing collaboration. Cognitive computing introduces technologies that emulate human cognition, enhancing reinforcement learning systems with capabilities such as natural language processing, pattern recognition, and adaptive learning. Cognitive agents and human-like decision making. Reinforcement learning involvement. RL agents make decisions based on rewards. Cognitive computing collaboration. Cognitive agents emulate human-like decision-making processes, allowing reinforcement learning models to incorporate cognitive elements into their decision strategies, potentially leading to more human-compatible and interpretable decisions. Natural language understanding in reinforcement learning. Reinforcement learning involvement. RL models interact with environments using actions. Cognitive computing collaboration. Natural language understanding (NLU) enables RL models to interpret and respond to human input, fostering more intuitive and versatile communication between reinforcement learning systems and users. Cognitive perception for enhanced sensing. Reinforcement learning involvement. RL models sense and perceive the environment. Cognitive computing collaboration. Cognitive perception technologies enhance RL systems' ability to interpret and understand complex environmental stimuli, improving the accuracy and richness of sensory information. Memory augmentation for cognitive recall, reinforcement learning involvement. RL models may use memory for experience replay, cognitive computing collaboration. Cognitive systems with memory augmentation enable RL models to recall past experiences and events, facilitating more context-aware decision-making and learning. Cognitive reasoning for complex problem solving. Reinforcement learning involvement. RL models learn to solve complex problems. Cognitive computing collaboration. Cognitive reasoning techniques provide reinforcement learning models with advanced problem solving abilities, allowing them to handle intricate scenarios with higher levels of abstraction and reasoning. Adaptive learning and cognitive flexibility. Reinforcement learning involvement. RL models adapt policies based on feedback. Cognitive computing collaboration. Adaptive learning in cognitive computing promotes cognitive flexibility, allowing reinforcement learning models to dynamically adjust their strategies based on evolving environmental conditions or user requirements. Cognitive computing platforms for reinforcement learning integration. Reinforcement learning involvement. RL frameworks define the structure for learning algorithms. Cognitive computing collaboration. Cognitive computing platforms provide the infrastructure and tools for seamless integration of RL models with cognitive capabilities, creating more powerful and intelligent systems. Emotion recognition in reinforcement learning interactions. Reinforcement learning involvement. RL models interact with users or environments. Cognitive computing collaboration. Emotion recognition technologies in cognitive computing enhance reinforcement learning interactions by enabling systems to recognize and respond to user emotions, creating a more empathetic and user-friendly experience. Cognitive automation for reinforcement learning decision support. Reinforcement learning involvement. RL models automate decision-making processes. Cognitive computing collaboration. Cognitive automation technologies provide reinforcement learning systems with decision support capabilities, assisting in complex decision-making scenarios and improving the overall robustness of RL models. Explainability and cognitive transparency. Reinforcement learning involvement. RL models may lack explainability. Cognitive computing collaboration. Cognitive systems emphasize transparency and explainability, allowing RL models to provide more interpretable and understandable justifications for their decisions. Cognitive computing for user feedback analysis. Reinforcement learning involvement. RL models learn from user feedback. Cognitive computing collaboration. Cognitive computing techniques analyze user feedback more comprehensively, enabling RL models to extract valuable insights and adapt their strategies based on nuanced user responses. Human-centric design principles. Reinforcement learning involvement. RL models aim for effective and human-compatible decision-making. Cognitive computing collaboration. Cognitive systems are designed with human-centric principles, ensuring that RL models integrated with these systems align with human values, preferences, and ethical considerations. Cognitive assistants for RL learning. Reinforcement learning involvement. RL models undergo learning processes. Cognitive computing collaboration. Cognitive assistants support RL learning by providing contextual information, suggestions, and guidance, enhancing the learning efficiency of RL models. Cross-model integration for sensory fusion. Reinforcement learning involvement. RL models integrate information from multiple sensors. Cognitive computing collaboration. Cross-model integration in cognitive computing allows RL models to fuse information from diverse sensory modalities, leading to more comprehensive and nuanced environmental awareness. Cognitive feedback loops for continuous improvement. Reinforcement learning involvement. RL models adapt based on feedback. Cognitive computing collaboration. Cognitive feedback loops facilitate continuous improvement in RL models, by incorporating insights from cognitive systems, fostering iterative learning and refinement. In summary, the collaboration between reinforcement learning and cognitive computing enhances the capabilities of RL systems by integrating human-like cognitive functions. This collaboration results in more intelligent, adaptive, and user-friendly systems capable of complex problem solving and effective interaction in diverse environments. Game theory. Reinforcement learning can collaborate with game theory to address strategic decision making in interactive and dynamic environments. Game theory provides a theoretical framework for studying interactions among rational decision makers, and when combined with reinforcement learning, it enables the development of intelligent agents capable of making optimal decisions in competitive or cooperative scenarios. Here is a comprehensive overview of how reinforcement learning collaborates with game theory. Introduction to game theory in reinforcement learning. Reinforcement learning involvement. RL focuses on learning optimal decision-making strategies. Game theory collaboration. Game theory provides a mathematical framework to analyze strategic interactions among multiple decision-making entities, allowing RL models to make informed decisions in competitive or cooperative environments, multi-agent environments, and strategic interactions. Reinforcement learning involvement. RL models often operate in multi-agent environments. Game theory collaboration. Game theory models interactions among multiple decision makers, aligning with RL scenarios involving strategic interactions among agents with potentially conflicting objectives. Nash equilibrium in RL decision spaces. Reinforcement learning involvement. RL models aim for optimal policies. Game theory collaboration. Nash equilibrium concepts from game theory can be applied to RL decision spaces, helping RL agents find stable strategies where no individual agent can unilaterally deviate to achieve a better outcome. Strategic decision making in RL policies. Reinforcement learning involvement. RL models optimize policies for decision making. Game theory collaboration. Game theory principles guide RL agents in developing strategic decision making policies, considering the potential actions and reactions of other decision makers in the environment. Cooperative game theory in multi-agent reinforcement learning. Reinforcement learning involvement. RL models may collaborate or compete with other agents. Game theory collaboration. Cooperative game theory concepts help RL models navigate collaborative scenarios, ensuring effective coordination and resource sharing among agents to achieve mutually beneficial outcomes. Competitive game theory for adversarial scenarios. Reinforcement learning involvement. RL models may face adversarial agents. Game theory collaboration. Competitive game theory informs reinforcement learning agents on strategies to counteract adversarial actions, fostering robust decision making in the face of strategic opposition. Repeated games and learning from iterative interactions. Reinforcement learning involvement. RL models learn from interactions over time. Game theory collaboration. Repeated game scenarios allow RL agents to learn and adapt strategies over multiple interactions, leveraging insights from both RL and game theory to achieve optimal long-term outcomes. Game theoretic analysis or RL reward structures. Reinforcement learning involvement. RL models optimize policies based on rewards. Game theory collaboration. Game theoretic analysis helps RL agents design reward structures that incentivize cooperation or competition among agents, aligning individual goals with overall system objectives. Evolutionary game theory for learning dynamics. Reinforcement learning involvement. RL models adapt and evolve over time. Game theory collaboration. Evolutionary game theory informs RL models about learning dynamics, facilitating the understanding of how strategies evolve and adapt in response to environmental changes or the actions of other agents. Mixed strategy Nash equilibrium in RL policies. Reinforcement learning involvement. RL models may incorporate exploration strategies. Game theory collaboration. Mixed strategy Nash equilibrium concepts allow RL agents to incorporate randomized or probabilistic actions into their policies, promoting exploration and adaptability in strategic decision making. Algorithmic mechanism design in RL environments. Reinforcement learning involvement. RL model operate in dynamic environments. Game theory collaboration. Algorithmic mechanism design principles from game theory assist RL models in designing mechanisms and incentives that encourage desirable behaviors among interacting agents in dynamic environments. Learning from observations in game theory. Reinforcement learning involvement. RL models learn from observations and experiences. Game theory collaboration. Learning from observations in game theory involves RL models adapting their strategies based on observed actions and outcomes, improving decision making through iterative learning. Coordinated exploration, exploitation in multi-agent RL. Reinforcement learning involvement. RL models balance exploration and exploitation. Game theory collaboration. Game theory informs RL agents on strategies for coordinating exploration and exploitation activities among multiple agents, optimizing the collective learning process. Game theoretic analysis of RL algorithm performance. Reinforcement learning involvement. RL algorithms aim for effective learning. Game theory collaboration. Game theoretic analysis evaluates the performance and stability of RL algorithms, providing insights into their behavior in various strategic scenarios. Game theoretic planning for RL agents. Reinforcement learning involvement. RL models plan actions based on current knowledge. Game theory collaboration. Game theoretic planning guides RL agents in anticipating the likely actions of other decision makers, enhancing their ability to make strategic plans in complex environments. Hierarchical game theory for RL coordination. Reinforcement learning involvement. RL models may operate hierarchically. Game theory collaboration. Hierarchical game theory principles enable RL agents to coordinate strategies at different levels of abstraction, facilitating efficient decision making in multi-level strategic interactions. In summary, the collaboration between reinforcement learning and game theory enhances the capabilities of RL models in strategic decision-making scenarios, fostering the development of intelligent agents capable of adapting to the dynamic and interactive nature of multi-agent environments. The integration of game theory principles provides valuable insights for designing robust and effective RL policies in a wide range of competitive and cooperative settings. Augmented reality AR and virtual reality VR. Reinforcement learning RL can collaborate with augmented reality and virtual reality to create immersive and adaptive environments. This collaboration leverages RL's ability to learn optimal decision-making strategies in dynamic scenarios, enhancing the user experience in AR and VR applications. Here is a comprehensive overview of how RL collaborates with AR VR. Introduction to RL in AR VR environments. Reinforcement learning involvement. RL optimizes decision-making policies. AR VR collaboration. RL enhances user experiences in AR VR by enabling intelligent agents to adapt and learn optimal behaviors within these immersive environments. Adaptive interaction and user engagement. Reinforcement learning involvement. RL models adapt to changing environments. AR VR collaboration. RL enables adaptive interaction in AR VR applications, optimizing content presentation, navigation, and user engagement based on user preferences and environmental changes. Dynamic content generation with RL. Reinforcement learning involvement. RL models learn to generate diverse and dynamic content. AR/VR collaboration. RL facilitates the dynamic generation of content in AR/VR scenarios, adapting virtual elements in response to user interactions and the evolving context. User-centric personalization in AR/VR. Reinforcement learning involvement. RL adapts policies based on user feedback. AR/VR collaboration. RL contributes to personalized AR/VR experiences by learning from user interactions, references, and feedback to tailor content and interactions to individual users. Navigation and path planning in virtual spaces. Reinforcement learning involvement. RL models optimize policies for navigation. AR/VR collaboration. RL enhances navigation and path planning in virtual environments, allowing intelligent agents to learn optimal routes and adapt to changes in the virtual space. Immersive learning environments with RL. Reinforcement learning involvement. RL supports learning through interactions. AR/VR collaboration. RL is applied to create immersive learning environments in AR/VR, where intelligent agents guide users through educational content, adapting to individual learning styles and progress. Spatial awareness and object recognition. Reinforcement learning involvement. RL models develop spatial awareness. AR/VR collaboration. RL contributes to spatial awareness and object recognition in AR/VR, allowing agents to adapt to changes in the virtual environment and interact intelligently with virtual objects. Real-time decision-making in AR/VR experiences. Reinforcement learning involvement. RL models make decisions in real time. AR/VR collaboration. RL enables real-time decision-making within AR/VR experiences, responding dynamically to user inputs, environmental changes, and interactive elements in virtual scenarios. Simulated environments for RL training. Reinforcement learning involvement. RL models undergo training in simulated environments. AR/VR collaboration. AR/VR technologies provide realistic simulated environments for RL model training, enabling agents to learn optimal behaviors before deployment in real-world scenarios. Multi-agent interaction in virtual worlds. Reinforcement learning involvement. RL models may operate in multi-agent scenarios. AR/VR collaboration. RL facilitates multi-agent interaction in virtual worlds, allowing intelligent agents to adapt and collaborate with other agents or virtual entities to achieve shared objectives. AR/VR based serious games with RL. Reinforcement learning involvement. RL models learn from serious gaming interactions. AR/VR collaboration. RL enhances serious games in AR/VR by adapting game dynamics, challenges, and scenario based on user performance, providing personalized and engaging experiences. Immersive storytelling with adaptive narratives. Reinforcement learning involvement. RL adapts narratives based on user choices. RL/VR collaboration. RL contributes to immersive storytelling in AR/VR by dynamically adjusting narratives and plot lines based on user decisions, creating personalized and interactive story experiences. Enhanced user feedback integration. Reinforcement learning involvement. RL models adapt based on user feedback. AR/VR collaboration. RL integrates user feedback from AR/VR experiences, refining decision-making policies and content generation to continually improve user satisfaction and engagement. Collaborative AR/VR experiences. Reinforcement learning involvement. RL models may collaborate with other agents or users. AR/VR collaboration. RL facilitates collaborative AR/VR experiences, allowing intelligent agents to adapt and coordinate actions with other agents or users for shared objectives or entertainment. Efficient resource utilization in VR environments. Reinforcement learning involvement. RL models optimize Resource usage. AR/VR collaboration. RL helps optimize resource utilization in VR environments, ensuring efficient rendering, dynamic content delivery, and intelligent allocation of computational resources for an optimal user experience. AR/VR teleoperation with RL guidance. Reinforcement learning involvement. RL models guide teleoperation. AR/VR collaboration. RL provides guidance for teleoperation in AR/VR scenarios, assisting user in remotely controlling devices or robotic systems within virtual environments. In summary, the collaboration between reinforcement learning and AR/VR technologies enriches users' experiences by enabling adaptive, immersive, and intelligent interactions within virtual environments. This synergy empowers intelligent agents to learn and adapt to user preferences, environmental changes, and dynamic content, creating compelling and personalized AR/VR experiences.